Hi, everybody. Welcome to Louis, Delaware. We call this little town the first town in the first state. And for this wonderful workshop, in this workshop, we try to look at the pathways connecting the climate signal to the deep ocean. And today, we have people from physical oceanography, marine biogeochemistry, and also marine ecosystem. And we hope over the next few days, we can share our knowledge and maybe for some collaborations to work together, try to find some better understanding and maybe solutions for one of the least understood part of the Earth's environment, that's the deep ocean. Welcome. Yeah.
Awesome.
Yeah.
All right. Yeah, just so we're the three co-chair, Xinfeng, Leslie, and I. And so if you have any questions, come talk to us. I guess Leslie will give the first introduction talk.
Yeah.
Awesome.
All right. So just some housekeeping rules. This is a very collaborative workshop, so let's all be nice to each other. Here's our code of conduct, QR code, if there are any issues. And in terms of our workshop philosophy, this is all about trying to strategically align all of our different groups and our different perspectives. And so what we want to do is we want to focus on the touch points between our communities. You are all experts in your own given field. We are all brilliant. And so we need to be looking at the touch points with each other and not deep diving down into our silos. And so hopefully we can find ways that we can align individual efforts toward the shared aims of figuring out these pathways and figuring out these gaps. And part of this is the challenge for each of us is to think big, think beyond anything that your one group or one discipline can work on, and try to think about those collaborative areas. And so to do that, we have to focus on being kind and open, listening to each other, focus on really listening, not about what you're going to say, but what other people are saying. Focus on elevating all the voices in the discussion. If you guys are in a breakout and you feel like one person is getting more bandwidth than others, help elevate those other voices and really focus on the yes and. And so acknowledging someone's point and then saying and a follow-on. I make my children play this game of yes and. So they're like, it's a car. No, it's a helicopter. It's really a pillow. I'm like, well, why can't it be a car and a helicopter? And they're like, what? So that you guys are focusing on making the couch cushions cars and helicopters over the next few days. So some notes, use the microphones. We have a lot of virtual attendees. Hello, everyone out in the virtual world. We're going to hold questions until the end of the talk. And we'll also be taking questions online. So if you're online, raise your Zoom hand. If you're in the room, I believe do we have a central mic? No, yes, we do have a central mic. I just can't see it from where I'm standing. So anyway, we'll go to the central mic. Stay on time. We have this. This will keep you on time. And don't forget the virtual poster presentations. Just a big thank you to all of the sponsors for the event. And now to dig into who we are, about 1/3 of us are mid to late career and 2/3 of us make up the early career and student realm. So this is super cool because if we think about next steps, maybe we come up with the next 10-year project, the next 20-year project. So that's super cool. We have so many folks early in their career here. We're about 2/3 in person, 1/3 online. And we have a wide range of expertise, which is super exciting because we need all of these bits and pieces to come together. So I'm going to open up my notes document here. So why are we here? What are we looking at? So we know that the ocean is taking up a substantial amount of excess heat from the atmosphere. And we know that some of it's making its way to the deep sea. We just don't really know how much. And so because this number isn't well constrained, we don't know what's going to happen in the deep sea ecosystems. Similarly, we know that the ocean is taking up 1/3 of excess carbon dioxide going into the atmosphere. And that's some of that CO2 is going to the deep sea. But again, we don't know how much. We also know that some of the CO2 making it down into the deep sea is in the form of CO2, and some of it is in the form of particulate organic carbon. We have a sediment carbon stock map over there. But again, we don't know how much and we don't know where it is. And so without these constraints, climate models have a big spread in depth, and these deep uncertainties may impose the strongest limits to our ocean predictability. So in order to improve our simulations, we need to reduce deep ocean uncertainties. So to summarize, we're here because of what we know. The deep ocean is diverse and fragile and changing in profound ways. We're here because of what we know we don't know, the scale of the impact of these changes. And we're here because we don't know what we don't know, because if we don't have a baseline for the deep ocean ecosystems and carbon chemistry, how can we possibly predict, manage, and mitigate what is going to happen next? So what is at stake here? There's a lot of super pressing challenges and impacts on the deep sea. We have anthropogenic pressures from fishing, from mining, from oil exploration. We have climate change impacts leading to acidification, deoxygenation, temperature increase. And then to fix climate change, we have MCDR strategies, which are also involving sinking of biomass or injection of carbon dioxide into the deep ocean. But then with that, we don't, like the deep sea is not very well included in the IPCC report because of all the gaps in knowledge. And Helen and a team just put together a gap analysis of AR6, the IPCC AR6 report, and they found over 200 times when it was mentioned that the deep sea was a knowledge gap. And so we couldn't conclude whether or not there was a climate change impact, which means that it's not part of the discussion. It's not getting to the summary for policymakers. So how are we expected to make a change if we just wave our hands and say, well, we don't know how bad it is? And so that's one of the reasons that we're here, is to find those touch points, because maybe we already know the answer, we're just not talking to each other. Or maybe it's as simple as sharing a bit of information or a bit of data across between observers and modelers in a new way that will lead to these gaps. And then on the top right up there, we have some text from the recent BBNJ, Biodiversity Beyond National Jurisdiction, also known as the High Seas Treaty. And most of the ocean is in these areas beyond national jurisdiction, these areas outside of EEZs, and over 90% of that ocean is deep sea. And so this is a really important element of it, and put into that text is, I've underlined it, including carbon cycling services that underpin the ocean's role in climate. And Lisa Levin, who will be giving the plenary later on today, was a key person in making sure that that language about the carbon cycle was included in the BBNJ treaty. And so the stakes are high, the need is pressing, but you guys are brilliant. So we're going to make this happen. So workshop goal today is we're focusing on the pathways connecting the surface to seafloor, looking across disciplines, across observing and modeling communities. And you're going to see this little schematic over and over again in terms of how things are going from surface to deep, but also the exchange between biology, biogeochemistry, and physics. So a lot of workshop aims. I'm really wishing this was a little bigger so I could read off of here. But to assess our current understanding of what we know right now. Whoa, who did that? No way, dude. And now I want $1 million. So we're looking to gather perspectives from the different disciplines, and also reviewing existing observation and modeling tools. So it might not be that we need to do more with what we have. Maybe we need to figure out new innovative ways to do observing or do modeling. And so from all of these discussions and knowledge sharing, we're going to develop a collective set of recommendations for how we can move forward. And then also our goal is to build an interdisciplinary network, because these recommendations are going to be interdisciplinary. And so we need a new network of people to try to accomplish them. So our agenda today is the overview day. Your brains will be bursting by the end. We're going to look at things in terms of physics, biogeochemistry, and biology, and from the lens of modeling and observing. We'll have a breakout session where we will discuss our current understanding of pathways. And this is both in terms of things that we know and that are really important for us to keep knowing and keep observing, and the things that we don't know. We'll have our keynote by Lisa Levin, and then we'll have a networking event in the evening. Tomorrow, we're going to cut it a different way. We're going to cut things in terms of slow pathways and fast pathways. And then we'll have our poster session, and then we're going to talk about observing and modeling methods. And then from that, then we'll have a breakout about the adequacy and gaps of existing tools to examine our pathways. You can see how this kind of all builds together. And then we'll hang out at Lewis Beach, informal hangout. And then Thursday is when we're going to put together our recommendations. So what do we need to do next in modeling and observing? And then the fun part, and you should be thinking about this the whole way, what is the next process study? Because you guys could all be co-PIs on the next big process study. So be thinking about these clever ideas for how we can all work together. Full agendas at the QR code. And this is a picture of a pathway to the Lewis Beach. So our workshop outcomes, we're hoping to do a lot of community building, which is why breakfasts and lunches and networking events are so important. Make new friends, new collaborators. We want all of the knowledge in your brains to review our current understanding, identify these set of needs, and then we're going to share the results with the broader community through a review paper. So after the workshop finishes, the co-chairs will get together and then we'll synthesize stuff and then ask if you guys would like to be a part of the review paper. Here's some Wi-Fi information. But you guys should have little things on your papers with Wi-Fi. So you're good there. Journal information. If you didn't know already, there was breakfast and too late, you missed it. But we're going to provide breakfast, lunch, and AM, PM coffee breaks. Here's some key people that can answer your questions. So Heather, May, Alyssa, and Mike, raise your hand and wave. Those are the people. Awesome. Let's see. In-person breakout assignments are posted within the workshop participant documents folder online, and you can follow folks on Twitter. And then Xinfeng, I don't know, do you want to speak a little bit about our fun activity in your hometown? Go on up.
Let's really mention that we're gonna have an informal outgoing on Wednesday afternoon. So that's the aim is to go to the Lewis Beach, that's also called Savannah Beach. It's very close to the inn many of you stay. After that, we're gonna have a gathering at the wheelhouse for group dinner. There are also a few places, if you have time, you can stop by. The first is Lewis downtown. It's like I mentioned, this is the first town of the first date. Actually, there are a lot of very old buildings. If I remember correctly, the oldest building in Lewis still standing from the 1600, so very old. It's pretty charming. There are a lot of little stores on the 2nd Street and a restaurant. Rehoboth Beach is a very popular tourist point in Delaware. It's about 20 minutes drive down Road 1. It's very charming, very nice, and it has a boardwalk, so that's a different part between the Lewis Beach and the Rehoboth Beach. And there, if you really like nature, we have a very nice state park. Cape Henlopen State Park is very big, has a couple of different ecosystems. There are trails on the dew, trails near the beach. Actually, there's I think Leslie, this picture, I took this picture out there. It's called the Point. It's actually the connecting point of the Delaware Bay and the Atlantic Ocean. So on the two sides, you're gonna see the two different water bodies. Yeah. Okay, those are really nice places if you have time to stop by them. Yeah. And if you have a question about those, just let me know.
Awesome. Okay. All right, great, thank you. So I think that wraps up our beginning talk. I think, are we still on time? This is fantastic. All right, so next up, do you have an agenda? All right, so next up, we're going to move into our talks. And we have Sarah Purkey online to do the talk, and Xinfeng is going to do the introductions for this session.
Okay, so the first part of this, the first session, as you can tell from the agenda, is overview about the physical, biogeochemical, and biological studies about the pathways. The first part of that is going to be about the physical, and the first talk, we're going to have two speakers talk about the observational part and also the modeling part. Our first speaker is Dr. Sarah Purkey from Scripps. She's going to talk about ventilating the deep, quantifying pathways of deep ocean ventilation from ocean observations. Sarah, already there?
Yes. Yes.
Oh, great. So, oh, great. All right, you can start. Thank you.
Okay. Great. Can someone in the room verify that I am screen sharing and that you can hear me?
We can see your face, but not your screen.
As you are sharing screen.
There we go. Now we can see your screen.
Oh, shoot. Of course. Just took a second. Okay. Sorry. Sharing screen again.
Okay, face and screen.
Okay, great. Thank you so much. Okay, well, first, thank you to the conveners for inviting me. I'm really sorry that I can't be there in person, but I appreciate the opportunity to present here. Yeah, so I was looking at the upcoming talks. I'm really excited about a number of the talks coming, so I'm hoping to kind of introduce some of the themes that I saw coming forward. And I was asked really to give an overview talk here. So hopefully as your first speaker, I can get us all on the same page, or at least start the discussion about what deep means, because I know to different communities, it means different things. Yeah, Leslie already gave a little bit of the motivation here, but just to motivate, I threw two kind of really critical points that I want to make here. The ocean is taking up a huge amount of the anthropogenic carbon and over 90% of the anthropogenic heat. And so the figure on the left shows that increase of anthropogenic carbon going into the ocean from a number of different estimates. And on the right shows the accumulation of heat in the entire climate system going into the ocean, land, ice, atmosphere, and uncertainty. And then the figures on the bottom show the distribution of where that carbon and heat are going from a few different estimates. And the main point here is just that the distribution of where the heat and carbon is going is not uniform throughout the ocean, and it really depends on ocean circulation and ocean ventilation, which is the point of this workshop, I think. And so, you know, small changes in ocean ventilation can have a really big impact on the amount of carbon and heat that the ocean can take up. So yeah, so I was asked to give a very overview talk. You know, this is really looking at the meridional overturning circulation. And here I'm primarily focused on the pathways of Antarctic bottom water and North Atlantic deep water. I am starting with two schematics of the meridional overturning circulation, a kind of newer one by Meredith that's over here on the right. With Antarctica in the center. And so I think as a community, we're kind of moving towards this view where we realize that the Southern Ocean is a very special and very important place where a lot of the global ventilation is happening. This schematic shows the lower limb, the Antarctic bottom water limb in that dark purple at the bottom, where we have deep water formation around Antarctica that circles around the ACC and then out into all three oceans. And then what I'm calling the deep, which is the North Atlantic limb, where we have North Atlantic deep water formed here in the North Atlantic, and then in yellow, the surface forcings. And then I'm also going to use this 2013 Lin-Talley schematic, which very nicely shows all the water masses to kind of help track where I am in the water column for this talk. And that's shown over here on the left. Hopefully everyone's familiar with this schematic, which again shows these kind of abyssal in dark blue, which is the Antarctic bottom water being formed around Antarctica in the North Atlantic deep water coming back. Okay, so Antarctic bottom water formation. This Antarctic bottom water is, as far as we know, produced in kind of 4 locations around Antarctica. We can see this in both the properties and tracers. And so this is 3 figures from a very recent Saldano et al. 2023 paper that was a nice review article about Antarctic bottom water. This is showing the temperature distribution near the bottom over on the left, the density, and then a figure showing the CFC concentration. So what we can see is that, as highlighted here, there are 4 primary regions. We have the Weddell Sea, the Ross, Adelie, and Cape Darley. That's over here. It's one of the newer regions where we've discovered deep water formation at Fritz Bay. And at all of these sites, we have particular conditions that allow for dense water formation. And what we can see is that it's very cold, it's very dense, and it carries kind of for atmospheric concentrations in tracers show that it's been recently ventilated. And then using a number of studies, we can see how the water flows out. It flows into these dryers in the Ross Sea and the Waddell, and then also into the Indian, shown in these pathways before moving north into all three ocean basins. So zooming into the conditions, I think thinking about when we think about ventilation is really important to understand the physical mechanisms that allow for dense water formation. And so for Antarctic bottom water, again, this is a recent schematic from the Silvano et al. Review paper showing what's happening on the shelves in these 4 regions where we have dense water formation. And so the important process here is that this is really a integrated system in that you need this special interaction between the ocean, sea ice, glacial ice, and the bathymetry really to get the conditions that we currently have to produce the Antarctic bottom water. And so starting on the top here, what's being shown is that you have sea ice production over the continental shelves. You get these really strong katabatic winds that are exporting the sea ice out of the region, which allows for these coastal plainias to open up. The opening of the coastal plainias allow for the exchange of heat, so we lose buoyancy via heat, and it also allows for the continued production of sea ice, which leaves behind this really salty water. That cold, salty water can then sink, and in a number of these locations, you have a situation that kind of looks like this, where you have a continental shelf with some kind of sill that allows for kind of the pooling of this very highly saline, very dense, very cold water that then circulates back towards by the glacier, which drives melting near the grounding line, and you end up getting this injection of relatively fresh, recently melted ice. Which creates a slightly less dense ice shelf water that sits over this high saline water that is eventually forced off the shelf and then really entrains the ambient waters that are sitting around before producing Antarctic bottom water and flowing out to the north. So as far as quantifying how much is being produced and its variability, the main ways that we do this is really in the Southern Ocean is through the properties and tracers that we see in downstream. Unlike the Northern Atlantic, I'm going to talk about in a second, it's very hard to constrain. The Southern Ocean is big, and so there's a number of studies that have done this, and they kind of estimate somewhere in the ballpark of 5 to 15 sphere drips of Antarctic bottom water being produced. The most kind of commonly used estimate is still standing from this Alex Orsi paper in 1999, which looked at CFC concentrations in the deep ocean, which is shown over here on the left. Again, so high CFCs are showing recently ventilated water. He took all the CFC data from MOSE and he mapped it to look at the ventilation rate into the deep ocean and found about 8 sphere drips, a rate of about 8 sphere drips of deep water formation. In the Southern Ocean, we do have some moorings, which can also give us a direct estimate of deep ocean ventilation. And I'm just picking kind of 2 that are over here, shown on this location to the star that's over here on the left. And the top one is showing the temperature, and the bottom is showing the volume of water that's crossing out of the Waddell to the north. And you can see that there is some variability in time in both properties and in the quantity. And then looking downstream towards the global circulation, we can see that that 8 sphere drips of water flows north into all ocean basins. This is a figure that from Johnson 2008, which which calculates the volume inventory of Antarctic bottom water, basically everywhere in the globe. And what we can see is that through most of the global ocean, Antarctic bottom water really fills the bottom few kilometers of the ocean. And so in places, when you look at the bottom to top, how much of the water column it's filling, it's really the majority of it. So this is showing in the Southern Ocean, it's kind of the bottom 4,000 kilometers, and really in the Indian and the Pacific, most of that deep ocean is been last ventilated in the Southern Ocean by Antarctic bottom water. And then highlighting another paper over here on the right by Chimoli et al. That started to look at the CFCs in the deep ocean to look at the pathways out of the Southern Ocean. And what this figure on the right shows, which I think actually Jake is going to talk a little bit more about tomorrow, it shows the arrival time, and so it shows the relative age of the Antarctic bottom water going to the north. And so a few things to note when we're looking to the north is that, you know, the first arrival time of these CFCs can be relatively fast. And we see a concentration of the CFCs in these deep western boundary currents that help bring that water from the south to the north. And so this is a section at 32 south, now looking at depth versus longitude. Oops. And what you can see in these kind of bright areas is the highlight of the CFCs arriving along these deep western boundary currents that are moving that Antarctic bottom water to the north relatively quickly. Okay, sorry, looking at the other pole in the North Atlantic, just going through North Atlantic deep water formation. A couple schematics here. So zooming out into the North Atlantic, we have the Gulf Stream in red coming to the north, bringing this relatively salty, warm water to the north. They're pulling this schematic a little bit further as that water moves to north of Iceland. You lose a lot of heat to the atmosphere, and that water is going to sink to create really, really dense water that sits here in the Greenland and in the Norwegian Sea. It overflows over the two cells at either side of Iceland, and here you can see mean from data taken across those cells looking at the temperature and salinity. And you see this dense water overflowing into the North Atlantic, which then entrains water to form that deep, lower North Atlantic deep water. In addition, in the Labrador Sea, we have kind of intermediate waters, the Labrador Sea deep water that's being produced. This is, you can see from a compilation of Argo floats, which is shown over here on the right. You have seasonal variability in the mixed layer depth and overturning that's happening in the Labrador Sea, which allows for the deep convection and deep ventilation down to kind of the 1,000 to 2,000 meters. And together, those deep and very bottom waters coming out of the North Atlantic are going to circulate in this, shown in the blue line, moving to the south. And so looking at where we are in this schematic, we can see this is the branch of the North Atlantic deep water, kind of returning water to the Southern Ocean. And again, looking at the Johnson paper, this is looking at the fraction of water along the North Atlantic deep water at 28.06 kilograms per meter squared. And you can see the water moving south in the Atlantic throughout the whole North Atlantic and then into the other basins along that isopycnol. And again, looking at the CFCs from Chimoli, you can look at along this kind of western side of the basin to look at the CFC concentration of along that the 28 kilograms per meter cubed North Atlantic deep water mass. And you can see the CFC concentration getting relatively low. The age distribution can also tell you something about the age, and that's just kind of shown over here on the bottom. which is the ventilation timescales, and also how that age distribution is spreading, which is an indication of mixing along that pathway. Okay, so bringing these things together, again, going back to the Johnson paper, we can see the relative distribution of the Antarctic bottom water and the North Atlantic deep water in the global ocean. On the top is the North Atlantic deep water versus the bottom of the Antarctic bottom water in the Atlantic and the Pacific. And we can see that throughout most of the ocean, or we can see this plume of North Atlantic deep water being produced in the North Atlantic and then coming south, eventually being upwelled in the ACC. And the Antarctic bottom water, which has no natural or no isopiconal outcrop and is formed in the Southern Ocean, and then fills most of the deep portions sitting below the North Atlantic deep water, and is eventually mixed away through mixing processes that I think we'll hear about tomorrow. And just to note that together, you know, these really set the ocean properties in the ocean, setting things like oxygen, not only temperature and salinity, but also oxygen and nutrients throughout the global ocean. And so when we think about the meridional overturning circulation, if we think about heat, oxygen, nutrients, or any of these other things, those ocean properties are really set by a balance between kind of the mixing and the evacuation of heat or other properties from above, and the ventilation of that cold, dense water coming from Antarctic and the North Atlantic. And so at any given time, the properties are going to, the internal properties are going to be set by that balance. And in general, we think of that process as being in steady state, where those two processes are in balance, and therefore the properties in the deep ocean should be stable. But one of the things that we've been noticing is that the deep ocean has been showing some variability over the last few decades. And so this study takes the repeated ship-based observations and looks at the deep ocean heat content below 4,000 meters. And so here what we're showing is the warming going on in the deep ocean in terms of watts per meter squared. The red here is indicating the deep basins that are warming, and we see that in the Southern Ocean we have relatively strong warming, but we see a propagation of this warming signal where everywhere that Antarctic bottom water is seen. And then in the North Atlantic, the long-term trend has still been cooling, although we have seen a lot more variability in the North Atlantic deep water. And so this study is using a linear rate of change over multiple decades, which we've seen is maybe not the best model for the North Atlantic. And just to note together, this is about 0.7 zetajoules per year, which is quite a bit of heat. Maybe not compared to the upper ocean, but if we look at for example, the atmosphere, yeah, so there's a lot of heat going into the deep ocean. Looking at this a different way, so again, looking at the heat over on the left, we can look at other changes in the ocean. And one of the things that we've noticed, or one of the leading theories, is that a lot of this warming in the deep ocean is not necessarily driven by advective heat into the deep ocean, but really driven by the fact that we are having changes in the formation rate of deep water ventilation. And so this figure over on the right in the middle is showing the changes in volume in meters of that Antarctic bottom water thickness. And so what we're seeing is a rate of about 100 meters per decade change in the amount of water that's being ventilated into the deep ocean. And if you have less cold water, but we hold the other processes constant, then we would expect kind of something similar to the warming signal that we've seen. In addition, we're also seeing an infusion of fresh water in the Antarctic bottom water. This is showing the freshwater flux. And then both of these things taken together are actually affecting the sea level because of the halosteric and thermosteric expansion of water. Okay, and then if we, I don't know what happened to the title there, but if we think about what is driving these changes in deep water ventilation, there's been a number of studies that look at the changes kind of close to Antarctica in a little more detail. And so this is 2 studies looking at the Australian Antarctic Basin, which is directly downstream from the Ross, the Indian, and the Adelie formation regions. And that's shown over here on the left and at the bottom, where we're seeing this kind of long-term trend in the salinity, going from back in the 70s where this bottom water used to be more salty and it's gotten fresher. And then we're also seeing a decline in the thickness. So that's shown over here on the right, and also in this study by Gunn over here on the left. And then last but not least, we are seeing changes in the properties such as oxygen, which are in line with the fact that we are potentially getting less ventilation in the deep ocean. And then in the Waddell, which is the other major part.
Timer just went off just to give you a heads up. You couldn't hear it because you're online, but just
Oh, great.
Thank you.
Thank you. I will start wrapping up here. In the Waddell, we're also seeing a decline. And these changes are kind of going back to the Ross, can go back to the shelf where we're seeing very strong freshening and changings that's being atmospherically driven. Okay, I will try to skip through this, but the Northern Atlantic deep water has also seen a fair amount of variability. This is one study that uses ship-based and Argo data to look at the temperature changes across the SCOSHIP line of the Northern Atlantic deep water coming down. And we've seen, just to say, a fair amount of variability in the Northern Atlantic deep water. Okay, sorry, and I ran out of time, so I'm actually just going to skip to the summary here. Basically, this was to introduce Antarctic bottom water in North Atlantic deep water, which is an important part of the climate system. You know, the rates are susceptible to climate change, and we've already seen some changes. And I just to say it's really important to monitor, and hopefully we'll have a lot of more time during this meeting to talk about what observations we need to monitor the deep ocean.
Thank you, Sarah. I guess we're gonna move to the next talk, and then after the second talk, we're gonna have a discussion together, Q&A together. Okay. So our second talk gonna be by Dr. Gokhan Danabasoglu. Okay. He's gonna talk about the physical modeling of the deep ocean challenges and opportunities. Thank you. Go ahead.
Well, thank you very much for this opportunity. So I'll be talking about challenges and opportunities related to physical modeling of the deep ocean. So this is the brief outline of the presentation. What I wanted to do here, touch on only a few basic sort of topics from the modeling world. And I'll be skipping on purpose some of the other sort of topics, such as deep ocean pathways. I think Izzy covered that in one of her presentations earlier, if I'm not mistaken. And if there's interest, we can chat about also additional topics such as the transport, model transport and simulated transport comparisons at the OSNAP array, for example. It has challenges as well. But in this presentation, I wanted to keep sort of, since the audience is quite wide here in terms of their expertise, I'll be touching upon only sort of main modeling challenges and related opportunities. So I'll be talking about global overturning circulation, representation of bathymetry, and particularly focusing on overflows in the models. I wanted to also remind people what the equilibration timescales are in the physical system, touching on approach to equilibrium and drift challenge that we have in the models, mixed air depths, and then finally, use of passive tracers. It was already shown some of it, in particular ideal H, CFC11, and helium isotopes that can be also used, and finish with some opportunities in my view. So you've seen various versions of this already, 2 or 3 versions from Sarah's talk, and I'm sure you'll see other versions of this simplified sketch of the global overturning system. What I wanted to, is this the, no, sorry, it's not. I wanted to show, go to the screen and show a few features here. The point of this plot that I'm showing here, twofold. One is to show sort of overall ventilation that Sarah talked about, particularly perhaps valid for the intermediate depths of the Pacific Ocean. But I wanted to highlight actually 4 points: Ross Sea, Weddell Sea, Labrador Sea, and Northern North Atlantic as the regions of deep convection. Deep convection is a form of ventilation, but ventilation is not necessarily deep convection. They are related. Convection does not necessarily imply net volume transport or mass transport across the column, but it clearly changes the deep ocean properties. So I'll touch on those later. In the modeling world, we actually go ahead and further simplify that sketch. And what I'm showing here is the residual, that's the both resolved and unresolved parameterized overturning circulation contributions. Left is the global one, and the right side is showing the Atlantic overturning circulation. And Sarah already talked about it. Usually this is the clockwise circulation. This cell is the Antarctic bottom water cell, counterclockwise circulation representation in the modeling world. And most of this global circulation occurs in the Atlantic. That's why we end up, and then associated heat and salt transports, we end up focusing mostly in the Atlantic Ocean, its variability and implications for prediction for intraannual to decadal time scales. And as Sarah already talked about, this cell in the modeling world, we usually associate that with the North Atlantic deep water, or we refer to it as the North Atlantic deep water cell. So I wanted to, these all look simplified. This is the bathymetry that we need to represent in the ocean models. And this is, I believe, the 1 minute eTopo1 topography. And it is rather challenging to represent the details of this bottom topography in a model. And this is showing a blow up of the Northern North Atlantic. You can see quite a lot of details there. You have fracture zones, you have narrow passages, you have so many islands. And furthermore, further blow up, you can see that there are so many bottom features, and then Charlie Gibbs fracture zone is here. And details matter, that I'm going to show one example of that. And this is showing the details of the Indonesian true flow region. Again, very many narrow channels, and they all matter, in particular in terms of how the water masses form and go further deep. I wanted to focus on here those 4 spots that I highlighted, connecting the sort of surface to deep. And those are the, well, before getting into that, I want to say that representation of the topography is rather ad hoc in the ocean models. Each group, each modeling center uses their own approach. You have to somehow represent the minimum, maximum, or statistics of the bottom topography, and there is no accepted best approach how to represent these things. And this might be actually a good opportunity. While it's a challenge, I'm reverting it to actually opportunity. Perhaps we need to get together as a modeling community or other communities to come up with best way how to essentially come up with a best practice approach to represent ocean bottom topography or bathymetry. These processes are usually not well documented or not documented at all. You cannot essentially track down how a particular bathymetry was created back in 15 years ago. And they are once you created and usually don't touch it, and they stay static for many, many years. And it involves quite a bit of trial and error. You create the bottom topography, you run the simulations, you look at the transport properties in the Sea of Japan or Mozambique Channel, and you get garbage. Because even though you have the right representation, in some areas, it is the cross-sectional area that matters. In some cases, it's the depth that matters. In some cases, it's the width of the strait that matters. So it is more or less trial and error. That's why you fix it once and you don't go back and retune or you change that thing. And details matter. So in our case, for example, we were having major issues with ventilating Northern Pacific. And we could not figure out what the cause of that is. Well, there's the Samoa Passage, right? We ended up essentially, we actually created the bottom topography, but it wasn't deep enough. By changing it one single grid point in that Samoa Passage area, you can essentially allow the ventilation in the North Pacific, of the North Pacific. So the details really matter in terms of what you do with the bottom topography in the ocean models. Now, these are the, Sarah already mentioned these overflow regions, and I'm just going to focus on, this is the North Atlantic, Greenland is to your left, Scotland and Iceland. We have the Therobank Channel overflow, and we have the Denmark Strait overflow. These are two important overflows in the North Atlantic, ventilating the, well, contributing to the North Atlantic deep water. So what do the models do? In some models, they are just bulldozed. There is no sill, and you just essentially make sure that you have enough depth in that in those sills so that actually the waters that are formed further north can come down. So some groups use terrain following coordinate systems in the hopes of essentially it reduces spurious entrainment. You can use partial shaped cell approaches. Going back to 1997, you can use bottom boundary layer schemes, but they are not particularly successful. You can use an overflow parametrization that I led the development of, that helps. Or you can use regional grid refinement. And these are techniques that you can sort of address these issues. It doesn't matter what you do with the bottom topography. It doesn't matter if you have the best overflow parametrization in the world. What matters is that if you do not have the correct source waters in the northern North Atlantic, there is no way for you to essentially produce the proper entrainment and proper product water. So the bottom line is that if the surface fluxes up there are not right or in error in some way, you will not get the proper source water properties. Consequently, you will not get the proper entrainment and the product water will not be there. So I said entrainment. Entrainment strongly depends upon the properties of the ambient waters that you are essentially bringing the product waters into the system. If your stratification is incorrect, which is likely the case, then you will not get the proper amount of entrainment. So not only the source waters, but the ambient stratification is so important for ventilating sort of formed waters further deep in the North Atlantic. Well, not just in the North Atlantic, it's the general case. So there is actually opportunity in this case to further address these challenges. Ross and Vidal-Sea overflows, as Sarah mentioned, these are the two regions where the Southern Ocean deep water formation occurs. These overflows are quite distinct from their Northern Hemisphere counterparts. They are shelf overflows. In the Northern Hemisphere, Ross, in the Denmark Strait and Fairbank Channel overflows, the partitioning of the source properties and the entrainment is roughly 1-to-1, and the product is 2. So if you have one source unit of source water, 1 unit of entrainment, you get 2 units of product water. It is quite challenging in the Southern Ocean to get the right properties of the product, because for every 1 unit of source water that you form, you get 4 units of entrainment. And guess what? In terms of not just the surface fluxes, but getting the stratification correct along the latitudes of the Southern Ocean is extremely challenging in the modeling world. And that directly impacts entrainment. Even with our overflow parametrization here, we get that thing 1-to-1 and we produce 2 units of product. So we cannot get the entrainment right in the Southern Ocean. So it's an important issue. It is actually saying that not the buoyancy fluxes only, but the momentum fluxes matter as well. And this is just to get back to representation. This is another representation of the overturning circulation. I'm showing it from 15 models in this case, in density space. This should be sigma 2 if I'm not mistaken. This tiny thing here is actually the cell associated with the Antarctic bottom water. In many of the models, Antarctic bottom water production is really small, and they don't necessarily penetrate further north. So that's a major challenge in the modeling world, and that needs to be addressed. And again, Sarah mentioned the North Atlantic deep water and Antarctic bottom water, and these are showing from 18 forced ocean models. This is from 2014, representation of the North Atlantic, or just simply what we call AMOC, Atlantic Meridional Overturning Circulation. Just to give you an idea about the shallow penetration depth of the North Atlantic deep water, this is associated again with the source water properties, entrainment properties. Product water gets too much diluted and it doesn't essentially inject it at the right depth. And I just arbitrarily drew a line at 4,000 meters just to give you an indication of how the models are doing. And the models are, in general, quite diverse in their representation of the depth of the North Atlantic deep water. If the North Atlantic deep water is not deep enough, Antarctic bottom water essentially fills the whole space. It becomes it goes to greater depths than it ought to. And this is the AMOC plots are from forced models, and I'm showing a recent study by Wilbert here, showing how the coupled models do in their representation at 26 degrees north, that's where the rapid area is, and also at 34 degrees south, that's where the Samba area is. The thick solid black line is the model average, and hopefully you can see the purple lines here. These are the purple lines. This is the rapid purple line, and Samba should be one of the purple lines here, actually. So, but if you look at the rapid side, you can see that the rapid estimate is going all the way to 4,000 meters. And in the modeling world, all the North Atlantic deep water, as measured by the zero crossing, is around 3,000 meters. So we are actually too shallow in the modeling world by about 1 kilometer. And that changes the ventilation properties at depth. And I wanted to now remind people what the equilibration time scale is in the models. Once you have once you have water masses below the mixed layer depth, mixing across density surfaces is extremely small. Scaling argument, this is a simple scaling argument. Its diffusion time scale is determined by a length scale squared divided by the vertical diffusivity coefficient. Once below the mixed layer, roughly you can take the length scale as 3,500 meters. And I actually use the generous mixing coefficient here, vertical mixing. You'll end up with order 4,000 years for equilibration time scale. Tidal mixing can certainly change that. And this is, we tend to use the Osborne relation to determine the tidal mixing. The catch is that some people indicate that, oh, our model reaches equilibrium a lot faster than 4,000 years. Well, there is an advective time scale, which is order 100 to 200 time scales. If you run the model, you may get a false equilibrium time scale, and you say, my model reached equilibrium in 200 years, which is not correct, because the diffusion time scale will tell you that it's order several thousand years. I put this equation on purpose here because many relationships in the physical world, or in the math world in this case, require some kind of regularization. I don't know what you mean. When I say regularization, do you know what it means? There is a division by n squared here. That's the stratification. What happens if n squared is 0 in a model, or if it is negative, right? You have to take care of that. What you do, how you take care of that, strongly impacts what you use for your tidal diffusion coefficient, and that impacts ventilation rate in a model quite significantly. And that's a major impact. And that's actually opportunity here. If anybody is in the audience really interested in revisiting the Osborne relation and coming up with a different formulation of that to eliminate such regularizations, that'll be very useful for the modelers. Bottom line for climate is that performing long equilibrium simulations are not practical at all, particularly at error resolving and permitting resolutions. And we must live with deep. I was a bit didn't know exactly what the title meant for the workshop, because to me, deep is 50 meters or 100 meters, because that's what the fishery people use. And that's why it's separated a deep and abyssal ocean, not being in equilibrium in most simulations. Okay, so believe it or not, I used to run these simulations really for a long time. And this is from one simulation for, if you look at the red line, 10,000 years, synchronously run at 3-degree resolution. What I wanted to show you here is that the top panel is the global mean for temperature. This is the deep mean temperature. Global mean salinity doesn't change because we use restoring. And deep salinity. This is the part that I was talking about. This red line, if you look at it, it takes literally several thousand years to reach a steady state. And this is the false equilibrium that I was talking about. People essentially run it for 200 or 300 years, and you reach this state and you say, my model is in equilibrium. It's not the case. If you run it longer, you'll essentially see that the diffusion time scale is kicking in. Approach to equilibrium in fully coupled systems strongly depends upon what the top of the atmosphere balance is. 95% of that shows up, that imbalance shows up in an ocean model. This is actually showing the TOA, top of the atmosphere heat fluxes that we get. This is from our CSM simulations, high top and low top, high top with vacuum. They are rather small because when we tune a coupled system, we wanted those fluxes to be ordered 0.1 watts per meter squared in absolute value or less. And this, we think that we achieved that. But if you run your model long enough, you can see that even a 0.03 watt per meter squared imbalance will result in actually quite substantial heat gain in the ocean. Oh my God. Okay, thank you. But even if you have zero imbalance, you need to be mindful of redistribution of all that heat in each ocean basin. This is showing the profile of temperature with respect to initial conditions, global, Atlantic, Pacific, and Southern Ocean. The upper ocean is exaggerated. You can see that even at zero imbalance, let's say, you will have redistribution and drifts within the ocean model. I'll skip this. Some people think that high-res actually solves this issue. Not in our case. Because high-res is essentially really difficult to come up with a balanced state at the top of the model. We have an imbalance of about 0.2 watts per meter squared, if I'm not mistaken, and that shows up as cooling within the ocean model. So that's a major challenge, tuning of the high-resolution systems. Mixed layer depths, okay. This is showing the, coming back to mixed layer issues. The upper part is from Argo, summer, winter, high-res, low-res, and summer for both hemispheres, winter for both hemispheres. You can see that if you look at the latitudes of the Southern Ocean, we do a lot better in high-res, and also we see better representation of the Labrador Sea. In the low-res, we tend to get too much deep water and too much ventilation in here, but with high-res, that's essentially eliminated. I wanted to just finish with saying that we use CFCs, and this is showing an example of that for both comparison to our model simulation. We do quite well, actually. Well, I shouldn't say this is the North Atlantic line. After being in the modeling business for over 30 years, I learned to trust observations, but I also learned to verify the observations. Trust but verify. I'm worried about this WOS. I mean, the models show essentially injection ventilation at the overflow depths. That doesn't appear to be the case in the WOS data set. I'm not sure. That's an interesting, actually, thing to look at. Pacific, we tend to underventilate. Finally, I wanted to actually, oops, why isn't this? Okay. The workshop topic is, in this case, was the surface pathways to deep, right? You can reverse the question, actually. What are the deep pathways from depth to the surface? And this is showing helium isotopes can be used for this purpose. Because helium, there are helium isotopes that were actually captured in the mantle when the Earth formed. And that is, those isotopes are being released at depth. So you can essentially use Newton-Krylov schemes to come up with essentially simulation of those helium isotopes. Then in return, you can essentially, you know where those helium isotopes are being essentially injected into that deep ocean. You can reverse this problem and say, where do they outcrop, or where do they essentially show up as surface fluxes? So it's the reverse question that this workshop is trying to answer. And Frank Bryan and colleagues actually have done that. These, for example, helium isotopes show up in these regions. So this is the reverse pathway. And then these ones actually show up primarily in the North Atlantic, but also in the Southern Ocean. Anyway, we can discuss more of these, but just the opportunities here, I sort of listed some challenges, but they can be used as opportunities as well, as I pointed out. I think we need deep Argo, not just in select places, but to the extent possible everywhere with biogeochemistry as well. So I wanted to advocate that. I'm a strong advocate for Argo, especially at depth. We need it for model initialization. We need it for prediction purposes. We need probably use of AI and machine learning techniques to accelerate equilibration in deep ocean, and maybe better connection between physics and biogeochemistry and others. And then, as I said, better connections between observationalists and modelers, but also across the communities. And with that, I'll stop. Thank you.
All right, so thank you both to Sarah and Gokhan for your talks. And now it's the Q&A period. So we can ask questions to both speakers. I was a little bit tickled on your discussion about, I don't know, how do we even define deep? So I'm the director of the Deep Ocean Observing Strategy. We're a United Nations Ocean Decade program, and we struggle to define it.
I got into trouble actually when I was actually talking to fish people. They say we need to get deep TNS properties correct. And as soon as I heard deep, I'm talking about like 1,000 meters.
Yeah.
They said, well, no. We need them at like shelf. They call the shelf 50 meters or 100 meters. That's their deep ocean.
Yeah.
Which is our shallow ocean.
Yeah.
It's difficult to.
Yeah, and our water column biologists are like, we want 200, the physicists 2,000. But then when we go to like the tech people, they're like, oh no, deep tech is 100. That's really hard. So audience members, question, and where is this mic and the central mic?
So can you comment a little bit more? You were talking about shelf overflow versus entrainment as a force. Which one dominates the source waters, and how do you get that number that you put out there?
So for the Fairbank Channel and Denmark Strait overflows, the ratio of theirs, it is coming from observational estimates. It's going. I can't even remember who were the observational folks at that point, but there. So for each unit of source water that you form north of the Nordic Seas, when they come down from Denmark Strait and Fairbank Channel, and there's split is, let's say, roughly, I don't know, 60% on the Denmark side and 40% on the Fairbank Channel side. Once they come down, hopefully without any numerical mixing or entrainment, when they reach the ambient waters, they should entrain roughly 1 unit of entrained water from that. And then the product water is roughly double. So it's 3 plus 6 injection of the product water. That's based on observational estimates. For the southern side, for the Ross Sea and Weddell Sea, it is again coming from, I don't know, maybe Sarah showed some of those observational estimates. It's 1 unit of water formed in the shelf. It is mixed with 4 additional units as it mixes and trains ambient waters, and comes out as 5 units. So that's roughly the ratio. That's, but I can't remember do you remember them, Lynn, observations? You don't, okay. There are, Sarah probably.
Yes, Sarah, you want to chime in?
Yeah. Sarah, do you know the observational estimate sources for those?
Well, I think like the Orsi one, thought it basically doubled. So there is, and that was from the CFC estimates. And then I think, there's some various studies, maybe Sonia Lake and some of the other ones. I mean, the recent study from the Orkney Passage, I don't know if there's anyone in the room that was really looking at the entrainment rates that were happening there, which is also, I think, one step beyond what you were talking about, which is the shelf formation and then further upstream. So I guess it depends on where you're calling the end of Antarctic bottom water, but yes, agree, there's a lot of entrainment.
And then another challenge is that there's a lot of open convection going on along the latitudes of the Southern Ocean, and those are difficult to get as well.
Hi, Gokhan. Thanks for the great talk. This is Charlie Stock from GFDL. Guys, going to ask you an intentionally provocative question to get some discussion. I guess, how much should we trust projections of deep ocean change from global climate models?
Not much, probably.
Could you break it down by depth horizon, maybe? Yeah.
Well, I mean, what I did not mention is that because of these drift issues, when we actually compute, for example, heat uptake by the ocean in the 20th century, we subtract linear trends of the control simulation from the 20th century trend so that we can get a sort of deep drifted estimate of the heat uptake. We have some discrepancies. If you trust the observations, maybe I should reverse that thing. I don't trust the observations either at depth. So no offense, Sarah and others. So, it's again, trust by verify in a sense. But in this case, I mean, they are so difficult to measure and they are so sparse. And the time scales in certain regions, like in the equatorial regions, it can essentially be order months that you can reach 4,000 meters. So it is, but again, I wouldn't trust necessarily models in their estimates either. I guess that's the short answer to your question.
The abyssal depths.
Yeah.
And then as you.
Well, I mean, the big example that I showed is essentially the shallow depth of the North Atlantic deep water, right? And that's a major issue that ventilates. So there are problems associated with that. If you look at the Antarctic bottom water, even if you have the right water getting there, it doesn't penetrate deep enough and it doesn't ventilate the North Pacific or North Atlantic. So those are all challenges. So we need to be really careful, I guess.
Yeah. And I think this is to the point why we need 2.5 days to dig into all this. We're just going to take one more quick question from the online team.
Yes, we see Jim Poterma. If you'd like to unmute and ask your question, go ahead.
Thanks. Hey, Gokhan. This is Jim Poterma at the University of Hawaii. I'm wondering if maybe you or Sarah can, kind of following on that last question, say something about the various reanalysis products, and presumably they're using assimilation to make some sort of statement about deep ocean properties. And any idea if they're making use of the observations, and if so, if that at all constrains it, or are these just simply being rejected by these assimilated models? Thanks.
So, I mean, I can, and then Sarah can chime in. In my experience, we have done quite a bit of data assimilation. That's why I was advocating for deep Argo. That's one reason. Deep Argo. The thing is that usually salinity observations are not that deep. Temperature can go up down to like 2,000 meters or something like that. But prior to Argo period, there's not much deep salinity measurements. And from our experience, our system, which is an ensemble Kalman filter system, it was rejecting pretty much a lot of stuff below 500 meters. So that essentially created differences. In a paper led by Alicia Karsbeck, I think came out in 2016 or something, we actually looked at reanalysis products, 6 to 8 reanalysis products, and they were all in their own world. They were essentially showing so much difference at depth that you could not use any one of them. And also, it's not just deep, because there are not that many observations near the coastal regions. And because of lack of observations, then your calculated pressure gradient is incorrect. And that was creating actually weird flow patterns as well. So those are all major challenges that we need to deal with.
That's great. Well, thank you guys so much. And Jim wins an award for asking a question at 3 a.m. in Hawaii. So congratulations to him. Yeah. I know. So one more round of applause for our physicists. So next up, we'll have paired talks from biogeochemistry. We have first up will be the observing talk, and Monique's going to introduce that, and then we'll have a biogeochemistry modeling talk. And if you wander, just grab one of these mics so you can wander and people online can hear you.
Yeah, so now we have two talks on biogeochemistry, and the first one is by Andrea Fassbender from NOAA PMEL from the observations perspective.
Awesome. Thanks, Monique. Thanks to the organizers for this opportunity to talk about ocean biogeochemistry. So my goal today is to kind of go over a few key characteristics of climate change reaching interior ocean biogeochemistry and largely focus on some of the tools and methods that are being used with sort of novel observing system tools to study these things. There we go. Okay, so to just dive in right away, I'll go over a couple things. First is one of the major changes to interior ocean biogeochemistry is coming in the form of deoxygenation. And so a majority of that, well, a smaller fraction of that signal is coming from the solubility of oxygen itself declining. As waters warm, they hold less gas. But additionally, changes to ocean circulation are changing ventilation times. And so more like 80% of the deoxygenation is coming from a lack of getting oxygen into the ocean and enhanced demand at depth where waters are not being ventilated as routinely. And this is, of course, important because a lot of organisms in the interior ocean depend on oxygen. This is a really nice example by Deutsch et al. Looking at the oxygen and temperature sensitivities of a couple organisms. In this case, I'm showing the summer flounder on the left and then the sea squirt on the right. And so the blue boxes are showing the occurrences, the histogram of the occurrences of these organisms within this oxygen temperature space. And then the lines that are shown, the lower one is showing the basal metabolic kind of thresholds for temperature and oxygen. And then the upper one is showing the active metabolic kind of thresholds. And as you can see, they're highly constrained by their sensitivities to temperature and oxygen and not in the same ways. And so this is just a really nice example of how species dependencies on environmental parameters can change over time in different ways that are going to cause kind of unknown ecosystem shifts at this point. Unknown to us at this point. And so I think more research in this vein would be quite useful. Another example is ocean acidification, which we've already heard a little bit about. This is some recent work that I led that was looking at interior ocean signals of ocean acidification. And one of the kind of shocking things that we found is that actually the largest signals for multiple metrics are in the ocean interior. And so here I'm showing on the left is the changes in PCO2 and the changes in the hydrogen ion concentration due to anthropogenic carbon accumulation alone to the year 2002. And you can kind of make out that you see larger changes in the interior in the mesopelagic, where you have lower anthropogenic carbon content. And to show this a little more clearly, on the right, I'm showing the exact same thing, but now the changes are relative to the average change in the upper 50 meters of overlying waters. So anywhere that's red is where you have a signal that's larger than the overlying waters. And for reference, the atmospheric CO2 change at this point was 92 microatmospheres. So the interior ocean changes are more than double the atmospheric forcing causing OA itself. And that's coming from, it's due to, I don't have time to do processes, but I would love to talk to you about them after, so come ask. It has to do with the buffering, weak buffering at depth. It is really terrifying. Agreed. And one of the other parameters we looked at was pH, and we did see some patchy signals suggesting amplified subsurface signals, but we couldn't quite make it out in the data product. But recent work by Kwiatkowski et al. Looking at CMIP6 models does indicate that indeed we should expect that pH changes will also be larger at depth than at the surface in many ocean regions. And this is just showing the depth of the maximum pH change by around 2100 across multiple CMIP models for SSP 8.5. And then the other kind of topic I wanted to bring up today is changes in biological productivity and export. Those can obviously translate changes into the ocean interior. And this is a paper by Barenfeld et al. In 2006, and multiple papers have come out since then using satellite data, just showing the relationship of declines in net primary production associated with warming. And in this case, they were focusing on the permanently stratified domains of the ocean. And again, if we look at the CMIP model findings, this is a figure again from Kwiatkowski et al. And it's showing the changes in NPP and the changes in SST, and the black symbols are from CMIP-5 and the color symbols are from CMIP-6. And you can see there is a relationship there of declining NPP with increasing temperature. But you'll also notice that there is like a very, very large spread. And if you actually look at the map of the expectations, this is the NPP change. This is the mean across models, and anywhere where you see stippling is where the models agree on sign. 80% of the models agree on sign. So anywhere without a dot means that the less than 80% of the models agree on sign. So kind of indicating that there's a lot more to learn in this area. Okay, so if we have a lot more to learn, one of the things we like to do, I'm an observationalist, is to turn to the observations. And we need an observing system for biogeochemistry that will help us learn more about what's going on so that we can get the right model parameterizations and have more, reliable projections that we can make decisions off of. And so one of the ways that people think about this is they often look at these time and space scale figures to think about, okay, how does our observing system cover what we need? And for climate, we're thinking about basin to global scale, and also, years to decades, so the upper right corner of the graph, which doesn't look too terrible. But one of the things that these diagrams is always missing is the depth component of the observing system. And so if we actually consider that, it's, thank you, it took a long time to make. As you can see, there's actually like a pretty big gap there, particularly on the months to decades time scale. So that's like extreme events to climate change, and on the sort of regional to global time scale. So we really do have a huge gap. And I should have mentioned, this is primarily the observing system this is the conventional observing system for temperature and carbon was what I modeled this after. So it might look a little different for your parameter of interest. If we add on our desired and hoped for autonomous observing system, we can start to fill in a lot of these gaps. With surface vehicles, steerable profilers, and then you'll notice that Core Deep and BGC Argo really fill a humongous space in this domain. So again, from the surface, looks kind of similar, but when you look at depth, there's a very large difference. And so today, I'm going to be talking a lot about BGC Argo. We just had some cheers for Deep Argo, but I have a lot of my group here, so BGC Argo, yeah, all right, thank you. And so to give a bit of background, BGC Argo, the goal is to have a 1,000 float global array. The current status is at about 54% implementation. But if you look more closely, really only about 2% of the floats carry all 6 of the parameters that we envisioned for the entire array. So that's pH, oxygen, nitrate, backscatter, chlorophyll fluorescence, and irradiance. So we still have a long ways to go. And in the United States, there have been some major contributions funded through NSF projects. And this is the SOCOM project, which has been renewed twice, and also the GoBGC effort, which is really implementing the US contribution to BGC Argo, which is 500 floats. So as this is growing, people are starting to do some really exciting things with the data, and we're starting to study ocean biogeochemistry in lots of new ways. And so I'm going to focus on 5 examples today, primarily focused on carbon cycling and biological productivity based on the prompt I was given for this talk. But there are lots of other things that I won't be able to touch on, and I'm going to put lists of citations in the slide because I think you'll be able to access these after the fact if you're interested to read up on other things. Okay, so the first example has to do with carbon stocks and bloom timing, and this is work being led by Adam Storr, who's a graduate student at Dalhousie, working with Katja Funnel. And they're using biooptical data from the BGC Argo array to look at the latitudinal patterns of particulate organic carbon stocks and also chlorophyll stocks to think about what the carbon chlorophyll ratios look like over large scales. They're also looking at bloom timing and the peak timing of the bloom. And so this upper right figure is showing the peak timing based on surface chlorophyll data, which is what we most commonly would use from satellites or other tools, versus the sort of integrated carbon stock, what that tells you about the peak timing and the bloom. And you can see that they're quite different. We're talking about a 15-week difference in the phenology for phytoplankton blooms, which has a lot of implications for higher trophic levels and how we understand food webs. So this is some pretty cool work that's in progress. My next example is related to estimating net primary production using float data and models that already exist for estimating primary production. And so I'm going to show an example. This is a float. You can kind of see the pink dots moving through the North Atlantic with the satellite ocean color chlorophyll A concentration in the background. And so what you can do is we can apply these existing models, in this case, the carbon-based productivity model, CBPM, You can apply that to satellite data. You can apply it to float data. It actually was developed using depth resolved information. And what you find is that the float and satellite actually agree pretty remarkably well for this particular example. But there are some places where the satellite data overestimate or underestimate the integrated net primary production, which is shown on top. And that has to do with the fact that when you apply the model to satellite data, you have to make some inferences about how homogeneous the mix layer is, whereas the floats are actually measuring inhomogeneities in the mix layer and below. And so you can get a bit more information that you can't get from satellites. Of course, the satellites have a much larger footprint. So the idea here is that we ultimately would want to combine satellite and float information to improve our ability to do net primary production based on the strengths of both tools. One other example for productivity here is from a paper by Johnson and Biff. This is just data directly from their table 1. It's showing the latitudinal pattern of multiple productivity models applied to satellite data, so VGPM, CBPM, and CAFE. And then in blue is showing estimates of net primary production based on diel cycles of oxygen derived from collating a bunch of float data together and estimating the daily rate and then scaling that up. And so there's a lot of differences in the methods here that I don't have time to get into, but there are very large differences in the NPP that we're getting from these two approaches. And so this sort of tells us that there's more to learn here, and we now should be using these other ways of getting at net primary production to complement what we have from satellites. And then, yeah, these are just references for later if you want to look at the slides. Okay, and so third example, there's 5, is about export magnitudes and mechanisms. So a lot of export estimates using float or autonomous data often come from tracer budgets. This is kind of a cool one that's relatively recent from Su et al., where they use floats and they have different biogeographical regions in the Southern Ocean. So in this case, the examples from the subantarctic zone. They collate the float data and then they look at the seasonal progression of oxygen subsurface. And so then they can infer how much respiration has occurred below the upper ocean and back out the annual net community production, which is a pretty neat, relatively new application. A few people have tried this in the past, but in a different way. So this is kind of something I wanted to highlight for getting at the magnitude of carbon export seasonally, or annually in this case. Another cool example relating to export mechanisms is some work by Zhang et al. And this is, they deployed a couple floats in the Western North Pacific and accidentally set them to profile every 1 day instead of 10 days, which is the routine cycle. And they like got a gem of a paper out of it because what they found is that really intermittent mixing events were causing the mixed layer pump to be really active in this region. And so in the mixed layer pump, you have a stratified route of water, you have productivity going on, and then you have an intermittent mixing event that brings a lot of that to depth. So you take carbon phytoplankton to depth, re-stratify, have more production, but then that carbon that's been moved to depth is more likely to be exported. And so when they looked at their float data, they found that on the one day cycling timescale, they identified multiple of these mixed layer pump events. But if they subsampled the data to a 10-day cycling, which is what normal Argo floats cycle on, you don't see any of the events. So it's just kind of a good reminder that these tools aren't like the catch-all for everything, but if you have an array of floats, you might be able to catch some of these events in a region. And again, there's tons of work in this area with floats. Okay, fourth example, this one is kind of near and dear to me. Even Wang led this work. He was a postdoc in my group, and he looked at Southern Ocean floats and estimated net community production using tracer budget approaches for multiple different tracers. And so DIC, nitrate, alkalinity, and then I'm not showing it, but also particle backscatter to do the POC budget. And by looking at multiple different tracers at the same time, which is one of the beauties of the floats, is they measure all these different parameters together, you can then do some fancy system of equations math and then back out the production of different biogenic carbon pools, which is pretty exciting. So from these float data, we were able to estimate PIC production, DOC production, and POC production well, he had done this once on one float in the North Pacific, but this was the first time we had done it at a large basin scale, which is pretty exciting. And then the bottom plot is just showing the comparison of our float-based estimates with a compilation of ship data from the region. And then the final example is work of Hannah Joy Warren, who's here and has a poster at this meeting. And what she is doing is she has built a database of phytoplankton taxa information and then used the BSAWC state estimate output to use some machine learning to map those distributions in space. So this is an example of the mapped diatom and Theocystis distributions in the Southern Ocean. And then she's using Gaussian mixture modeling with Argo float data to differentiate biophysically similar regions, as are shown here in the colors, and then is looking at the DIC concentrations in those different regions and kind of looking at overlaps between the phytoplankton, taxa, and the carbon concentrations. And it's much more detailed than that, so talk to her. But I just really wanted to show it's really exciting work. I'm a biogeochemist for sure, and I think about black boxes, and she's actually trying to get the organisms doing the work connected to the carbon cycling, which is pretty cool. She's a biologist, clearly. And then again, some other useful resources for those interested. Okay, so even though the BGC array is not complete, we are amassing a lot of observations over time, and we're already being able to do some really cool work. And so if we look at the actual array distribution, the total number of delayed mode quality controlled oxygen profiles is shown in the bottom right. The amassing of oxygen is shown in the video. And then the upper right is showing all non-Argo observations in the World Ocean Database for oxygen, chlorophyll, and nitrate pH. And you can see that Argo is essentially overtaking that and is becoming one of our primary means of getting biogeochemical data for the ocean interior. These are profiles to at least 1,000 meters. Okay, so what I want to do now is step through, with all this data, there are some efforts going on to synthesize them into gap-filled products that make the data a bit more accessible to other communities and for other applications. So I'm going to go through two examples, even though there are more, of the data synthesis. And the first is work by Raphael Saouzid. She's really been a leader in this area for BGC Argo for quite a while. And so what she's doing is taking satellite and float data and training machine learning models to predict chlorophyll and particulate organic carbon through depth, and then using ARMOR 3D fields to help do the mapping. And so what she ends up with are these 4-dimensional chlorophyll A and POC data products. And currently they're available at 1/4 degree resolution for the upper 1,000 meters, and they're moving to higher resolution very soon. And so this is very exciting stuff that's going on at LOV. The second one I want to talk about is led by John Sharp, who's a member of our lab, and he's using float and ship data to train machine learning models to predict oxygen, and then he's applying that to temperature and salinity gap-filled products, and then mapping oxygen in 4 dimensions. And he's done this currently at 1 degree resolution for the upper 2,000 meters over about 20 years. And so these are really exciting new compilations that make the data a little bit more accessible for people outside of Argo to work with. And so I'm just going to step through very few examples, and depending on how much time I have left, of applications with this. And so the first one is related to species distribution modeling. So this is work led by Mary Margaret Stoll, who's a graduate student in our group. And one of the things that people are often do for species distribution modeling is use surface satellite chlorophyll information as a way to help predict where a species might be migrating throughout the year. But by integrating these depth resolved and time resolved Argo-based data products, we can actually start looking at interior ocean information. So oxygen distributions, temperature with depth, and also productivity hotspots below the surface and below the view of satellites. And so because of that, we can start looking at these 3-dimensional, seasonal, or higher resolution species distribution maps. And this is some exciting work that we are trying to get done. Okay, might be my last example based on time, is for these data products can be useful in model benchmarking. So one of the ways that we validate interior ocean characteristics in the models we use to make future projections or hindcasts is using either time series data or compilations of ship data that are fixed in time. It's just like a climatology. And so here's an example where we have one Earth system model showing oxygen at 200 meters depth, and then on the right is showing the difference between the GLODAP gridded product oxygen and that model, and then below that is similar information, but it's just a transect through the North Pacific. So you can see that there are some discrepancies, but that's really all we have. With new products like the Go by Oxygen product, we can actually start looking at these discrepancies over time. And here I'm just showing it on an annual time step, but you could do this on a monthly time step, which might really help us start to figure out some of the issues with biogeochemical models or ecosystem models that many people are working on to get better predictions, which is going to be really useful for things like ecosystem-based management or also understanding the impacts of MCDR strategies. I think I have time. Okay, my last example is also thinking about the global carbon budget, which is estimated annually using global ocean biogeochemistry models and also these CO2 flux data products shown in teal and purple. And as you can see, over the past about 2 decades, they've been diverging. And so our central estimate for the annual ocean carbon sink is in black. And of course, we also have hydrographic-based estimates of anthropogenic carbon, but there is a decadal latency, which makes it difficult to help solve this particular problem. And so one of the things that would be useful is independent estimates of the ocean carbon sink, which do exist, but aren't yet incorporated into the global carbon budget. And one of those that's kind of on the horizon is the use of Argo-based data products for carbon cycle reconstructions. And so a very kind of coarse example of this is to apply the Go by Oxygen product with these tools called ESPERs that Brendan Carter has developed to estimate carbon. So this is just one example showing surface dissolved inorganic carbon over time. But we are working on more complicated data product development in this space, as are other people, which I think will be really interesting over the next 5 years to see how that, if that helps provide other constraints on the anthropogenic carbon sink. So just to conclude, so close, is I just want to make the point that I think Argo in general and BGC Argo are filling a really important gap in the observing system. But there's some kind of not great news I have to share, which is that sustained funding for US BGC Argo does not exist beside a few pilot arrays. So NOAA is funding a few pilot arrays, which is great, but there's no real big funding going on. The only funding we have is NSF, and the Go BGC project will conclude in 2026. And SOCOM is up for renewal, but they haven't heard yet. So there is essentially a cliff in BGC Argo float deployments in 2 years. And so if you think that these platforms could potentially be valuable for your research, I would very much urge you to consider writing a proposal to NSF. They're very happy to fund like float projects. And you could do that to either use the data or deploy more floats. And if you wanted to do any deployments, just collaborate with one of the US float deploying institutions. They'll reduce the burden on your life. Trust me. Okay, thank you.
Thank you very much. We move to the next talk. It's going to be from Dr. Tim Devries from UCSB. Okay, his talk going to be pathways of organic carbon export and the sequestration by the biological.
Yes, thank you. Thanks for having. Yeah, like I said, thanks for having me. Apologize for the glow around my head, which appeared, and the lighting is not very good in this room. Okay, so yeah, I'm going to be talking about pathways of carbon export and sequestration by the biological pump. So the biological pump, of course, connects the surface and deep ocean, which is why it's we're talking about it in this this workshop here. So as illustrated in the figures here, the gradient between the surface and deep ocean, DIC, is to a large degree driven by the biological pump. So if you kind of take the observed DIC as shown here in an example from the Northeast Pacific off the coast of California, and you subtract off the DIC that would be in equilibrium with a pre-industrial atmosphere, and then you add a little bit of anthropogenic CO2, the difference is due to the biological pump, which I'm referring to mean the soft tissue pump, and then also a little bit of the calcium carbonate pump as well, which I won't cover in this talk. But the little bit of calcium carbonate pump can be estimated from alkalinity, and you see that the remainder is due to the soft tissue pump or the biological pump. So about 2/3 of the surface to deep gradient is due to this biological pump, and that's connecting the surface and deep ocean by biological and physical transport processes. So before I jump into the pathways that this biological pump works through, just a few definitions here so that we're all on the same page. So I'll talk about carbon export as the vertical flux of organic carbon past a fixed depth horizon. And typically that's the base of the euphotic zone or maybe a fixed depth such as 100 meters. That's expressed as a rate, for example, globally integrated in gigatons of carbon per year. Carbon sequestration is the buildup of respired DIC or biogenic DIC. As that carbon is exported, it's respired by bacteria and animals, and then that DIC builds up below the surface. The buildup of that DIC below the surface is the carbon sequestration, expressed as an inventory in gigatons carbon, for example. And then the sequestration time is essentially the ratio between the sequestration inventory and the carbon export, and that's the time that it takes for that biogenic DIC to resurface to the euphotic zone. So that, of course, is driven by the transport from upwelling. That's physically transporting the biogenic DIC back to the surface. So that's expressed as a time scale. So the time scales here are, the very fast time scale of carbon export and sinking to the deep ocean, and then the much slower time scale of resurfacing of DIC in these upwelling currents. So the pathways, which is the focus of this talk. There's various ways one can break these pathways down, but I've broken them down into 3 pathways just to keep it simple. So the first being the mixing pump. So that's just the physical transport of organic carbon by ocean circulation and mixing. For example, as Andrea gave an example in the last talk of the seasonal deepening and shoaling of the mix layer, and that detrains some organic carbon into the deeper layers. Also, just large-scale circulation will also move organic carbon from the surface to the deep ocean, and eddy mixing because there's just more organic carbon in the surface ocean. So all of that mixing just moves to mix that organic carbon down. The second pump is, or the second pathway, I guess, is the migrant pump. So that's driven by the vertical migrations of animals such as zooplankton and fish. They'll come to the surface in the nighttime to feed, in the nighttime to avoid predators, and then they'll go back down during the daytime and bring that organic carbon that they ate that's now trapped in their bodies to the deeper ocean, and that's a mechanism of export as well. And then the gravitational pump, which is simply the gravitational settling of stuff. So phytoplankton aggregates or fecal pellets, carcasses of animals, right? So these are the pathways. And how are these represented in models, and how well are they represented in models? The mixing pump is essentially represented in all models that have mixing, which any model that has a circulation component will have that, to various degrees. What's also needed to represent the mixing pump is a representation of the forms of carbon that are preferentially mixed down. So these tend to be the suspended pools or dissolved pools of carbon. And then, of course, it helps to represent the small scale processes that can act on these carbon pools to mix them downward. So, many models are coarse resolution. They don't represent the small scale processes, so they're not getting all of these processes. But again, all models that have a circulation component are getting at least some of this mixing pump. The migrant pump is typically not represented in your standard like ocean biogeochemical models. It likely will be in kind of the next generation models because there's just so much interest in representing this pathway. And folks have determined that it's a significant pathway of carbon export. There are a few models out there that do represent it now. And again, it will become more standard in the future. The gravitational pump has been known about for decades, and that's basically in all models to, again, different degrees. So the simplest models will just have a single sinking POC pool, detrital pool, and then maybe vary its speed with depth or viscosity. More complex models will have more pools of sinking POC. And then, of course, what's another important part of the gravitational pump is the respiration component. So that is generally you have bacterial respiration and then sometimes also zooplankton feeding on these sinking POC as it sinks through the water column as well. Some models also have representations of mineral ballast that affect the gravitational pump as well. So here's a list of kind of previous models, model/data-based estimates. So they're all models. They're data-based to the degree that the models are kind of adjusted to achieve some agreement with some observations. And these are examples of estimates of mainly the export of these different biological pump components. So you see that most of these either empirical or mechanistic models are focused on estimating the export of organic carbon. There's been less emphasis on looking at the sequestration and then the sequestration time. But kind of a jumping off point for what I'm going to show you here is this last row here. So this literature summary by Boyd et al. In 2019. Their paper was called The Particle Injection Pumps. So they estimated, based on the literature summary, the export, sequestration, and sequestration time of different pathways. But it wasn't constrained by any data, essentially. It was just kind of an estimate based on the literature. So that's a jumping off point for the work I'm mainly going to talk about, which is from the paper of Nowicki et al. In 2022. And this is a model that basically assimilated some data sets to try to provide kind of, more certain estimates of these export, sequestration, and sequestration time. So that's what I'll focus on here. So the model is based first on this satellite-driven implicit ecosystem model, or simple model, from Devries and Weber, which is diagrammed in the upper left there. And what Michael Nowicki, who is one of my graduate students, did is embed an actual ecosystem model in there with zooplankton and their migrations. And then the model is basically trained by adjusting the model parameters to match some observations. So some of the observations are shown in the bottom left here. Those include dissolved oxygen, DOC, and POC flux. We also trained the model to represent the zooplankton and phytoplankton biomass as well from different data compilations. So cheers to all the observing systems for all the data that goes into this model here. So here's kind of a schematic summary of what we get in the end. And by the way, 124 different models were run, and that's how we get some basically uncertainties in the fluxes that we see here. So the gravitational pump, based on this kind of data model fusion synthesis here, is about 7 gigatons per year. And that's roughly composed of about 80% fecal pellets of zooplankton and 20% phytoplankton aggregates. It's sequestering about 1,000 gigatons of carbon, and the sequestration time is roughly 150 years. One caveat here is that fish, higher trophic levels, basically other than zooplankton, are not included here. So fish are not represented in the model. We think that their export is probably subsumed under these zooplankton fecal pellets in the model. The different pathways of the gravitational pump here relative to the total export, you can see that these fecal pellets of zooplankton dominate the export in the kind of lower latitudes, whereas the phytoplankton aggregates become more important where you have higher productivity, such as along coastlines, and then in the subpolar regions, particularly the subpolar North Pacific and North Atlantic there. The mixing pump. We find that about 2 or so gigatons of carbon are exported by mixing. This in the model would be the semi-labile and more refractory, semi-labile, semi-refractory DOC. There is some labile DOC or suspended POC in there, but we don't bother counting that because it's just sequestered for so short. It really doesn't build up to an appreciable inventory. But we get an inventory of about 100 gigatons of carbon. And this gives a sequestration time of roughly about 50 years for this mixing pump. So in terms of sequestration time, it's the shortest or the weakest of all the pumps, even though it can export an appreciable amount of carbon. The sequestration time of that carbon is rather short. In terms of where that pump is important, you see in the diagram here. So again, this is the mixing pump export relative to the total export. And you see it's mainly important where we have, in this model, water is being subducted into the interior. So mode water formation regions, intermediate water formation regions, and deep water formation regions as well. Mainly the first two, the mode and intermediate water formation regions. I should caveat this as well. Everything gets a caveat here. The model doesn't represent the seasonal fixed layer pump because it simply doesn't have seasonality. It's just a steady state climatological circulation. Also, the eddy subduction pump really isn't explicitly resolved, but thought to be small based on other work. So this is just basically the very small scale mixing processes that aren't captured by this model because it's a coarse resolution about 2 degrees in the horizontal resolution model. So it doesn't resolve those mixing components. The migrant pump ends up being about 1 gigaton of carbon export, sequestering 150 gigatons carbon, so that's easy math. Sequestration time is about 150 years. So that's mainly determined by the depth to which these organisms are migrating, which is around 400 meters or so on average. Caveat there is that we don't include seasonal migrations in this model. We only include the daily migrations. Also, we don't include fish, as I mentioned before, so just zooplankton. So where is this important? It's mainly important where we have in the model these zooplankton that can migrate. They're the larger zooplankton, so they tend to occur in the places where there's larger phytoplankton because that's what they feed on. So generally the higher latitude regions and the coastal regions where there's high productivity. And definitely not in the subtropical gyres, which is a little puzzling to us that there's another satellite LiDAR-based observations that indicate there's actually a lot of migrating organisms in the subtropical gyres. So we have to basically, we have differing opinions on where the migrant pump export is the most important. But in this model, they're not able to support migrants in the subtropical gyres because there's just not the food to feed them there. Since we're talking about the deep ocean in this workshop, I thought I'd show the depth distribution of the sequestration and the respiration and export. So this is from Siegel et al. 2023, review paper in Annual Reviews of Marine Science. And so the left-hand panel there shows the respiration rate of the carbon that's exported by these different pathways. And you can see it's basically exponentially decreasing with depth. This is a log scale on the x-axis there. And then the middle axis shows the sequestration time in different basins here, Atlantic, Pacific, and global. And that increases with depth, of course. It takes water at depth, deeper depths longer to reach back to the surface. And then on the right-hand panel here, this is basically the convolution of these left two. That's the total sequestration, carbon sequestration. And there you see that the carbon sequestration is peaking in kind of in the mesopelagic layer, essentially reaches a maximum between like 200 to 400 meters. So it turns out that about 50% of the carbon that is sequestered in the ocean is due to respiration above 1,000 meters, and 50% is due to respiration below 1,000 meters. There was a recent paper written on that, recently published by Louis Legendre and authors in Nature Geoscience. One last thing here is that air-sea disequilibrium also plays a role in setting the magnitude of the biological pump. So a recent paper, again, by my student Michael Nowicki in 2024, basically coupled the model that I just showed you to an interactive atmosphere and then ran experiments with instantaneous gas exchange and with realistic gas exchange. So if we take the difference between those experiments, we can see the effects of the air-sea disequilibrium of CO2. And basically what it does is it tends to increase the carbon that's sequestered in the ocean by the biological pump because it prevents the outgassing of upwelled biogenic DIC. So on the left map here, what you're seeing in the colors is the carbon sequestration within each water column of the ocean in this model. And where it's red, that means that carbon sequestration is enhanced by air-sea CO2 disequilibrium. And where it's blue, that means that carbon sequestration is reduced by air-sea CO2 disequilibrium. So it's almost everywhere enhanced by this disequilibrium, except in these deep water formation regions, Labrador Sea, Greenland, Iceland, Norwegian Sea, and along the Antarctic margin. That's where deep waters are forming. And the disequilibrium prevents the ingassing of CO2 in response to biological activity. And then those waters are subducted before they can take up as much CO2 as they possibly could. But everywhere else, it's essentially preventing the outgassing of upwelled CO2. And so it's thereby enhancing the biological pump. Here on this side.
This is Leslie. We just hit our 20 minutes if you want to wrap on that.
Oh, okay, yeah. So this is the sequestration time here. Yeah, so that is a wrap up. So there's a summary just of the numbers from this series of models, and a thank you. So thanks.
That was perfect. If I waited 10 more seconds, right? So big thank you to our biogeochemists. And Andrea, if you want to come on down back up front, we'll do a little bit of a Q&A before the coffee break. You can stay on the podium if you want.
Thanks for the nice talks.
Good. So, Michael.
Oh. Yeah, I have a question for Andrea. For the machine learning gap-filled data products, does that come with uncertainties? And I guess how much can we trust this really fine scale variability in these outputs?
That's a good question. I'm less familiar with the details of the French data product uncertainties. I think they're working on an updated paper on that will describe them. For the oxygen-based product, John did run, he trained the model or trained the algorithms using model data. So he essentially did an OSSI on it to get an estimate of the mapping uncertainty. And then we include observational uncertainty as well. And binning uncertainty. So it has an estimate. I think that in the next round, the plan is to do OSSIs across multiple models to get a better estimate of the mapping uncertainty. So we're trying to do our best there for that product in particular. Some of the others I can't really speak to.
This my question for Tim. This is Wei Chun Kai. What is there a role of conversion between POC and DOC in your model? And yeah, I'll let you. Your model, do you is there a continuous conversion of micro reaction on POC to DOC, particularly refractory DOC?
Yeah, there is. There's basically 4 pools of DOC. And those are basically being converted from the more labile forms to the more refractory forms all the time. And then there's two pools of POC, and the small pool, the small POC is being dissolved continually into labile and semi-labile DOC. So there's a POC to DOC conversion, as well as conversion from more labile forms of DOC to more refractory forms of DOC.
Ask just a follow-up thing. Your time scale is that it's about 50 years. So that seems to suggest that refractory organic carbon is a rather small thing.
So that's that 50 years is for the sequestration of biogenic DIC. So that's the DIC that's respired from DOC below the surface, and then it's held below the surface before it resurfaces. So that is not the inventory or sequestration time of refractory DOC. So in the model, there's about, roughly 700 and something gigatons of refractory DOC, which I didn't talk about at all. Apologies.
Yeah. Oh, yeah, Lintella here from Scripps. Andrea, thank you for that talk. I guess I had actually I have more of a comment, which is I want to really amplify that last statement you made about the issues with funding for BGC Argo. 2026 is actually the no-cost extension period. We stop I'm one of the PIs in that program. We stop acquiring floats July 31st, 2025. That's only a little more than a year from now. We have no funding beyond that. So if this is a product that, and most of those floats have 5 sensors, they're just missing the downwelling irradiance, which is coming in now. And I know that's a problem for primary productivity calculations. It's happening, but the other 5 sensors are on those. All the floats can have it now and are having it in the next set. It was just a matter of tech development. Anything you can do to bring pressure, if you know program managers, if you're on interagency panels, if you're anywhere, highlight, and if this is an important data set to you, I think that you've really highlighted the exploding amount of work, and especially your group is amazing, on looking at the global analyses as the data come in. Do it.
Yes, we have a question from Lisa Levin. Lisa, you can go ahead and unmute.
Hi, Lisa.
Hi. Thank you both for really interesting presentations. My question's for Andrea, and it's really, I was wondering, what is the GoBio-02 database? And are you familiar with the Global Ocean Oxygen Database and Atlas being produced by the Global Ocean Oxygen Network, the IOC group? And are they the same thing, or are they different?
See here. So GoBio is based on GLODAP oxygen data and float oxygen data only. I am aware of like the World Ocean Atlas product that I think was recently released, I believe. Looking around at people. Okay, yeah, thank you. I'm not sure, is that the same as what you're talking about, or are you talking about a different one?
There's another one. It's being led by Vera Garçon and Marie-Laure Gregoire, but it's part of the Global Ocean Oxygen Decade program, which is part of the GON, the Global Ocean Oxygen Network. But it would be really useful to have a conversation between the two. I know the GON one includes coastal oxygen values as well as open ocean.
Yeah, that would be great to definitely touch base. And I didn't mention, I should have mentioned to the first question, John Sharp and Raphael Sauzid are actually leading a SCORE working group on Argo-based data product development to try to develop recommended practices to improve and make sure people are doing things consistently and developing data sets that others can then run through their model to do comparisons and also have uncertainty. So there's like a community-wide, international community-wide effort to try to do this well.
For oxygen, is that?
In general, but so I was just kind of, that was sort of a response to the first question, but yeah, Lisa, we should touch base for sure. That'd be great.
Thank you.
Awesome. Let's do one last question.
This is Tim Yang from UW. So Tim, I'm curious about your global map when you show migrant pump is only a small fraction of total export in the subtropical gyre, but you did show the fecal pellets account for about 80 to 90% of the gravitational pump in the subtropical gyre. So how do you what do you think?
Yeah. So those are in the model, there's small zooplankton and large zooplankton. So the ones that are prevalent in the subtropical gyres are the small ones. And those in our model don't migrate. I believe there's, the fact that we're missing probably the higher trophic levels could maybe explain that there would be more migration in the subtropical gyres of like fish, for example. But yeah, basically our model just doesn't have the capability to support migration in the subtropical gyres because the plankton sizes are too small. And we don't have those large zooplankton that migrate essentially. So maybe it's the higher trophic levels.
So thank you everyone for your questions. I know there's so many, but don't worry, we have a panel discussion with all our speakers. Let's applaud our biogeochemists. And next up, we're going into a coffee break. I'm going to keep us on time. We're starting 5 minutes late, but tough cookies. You still got to be back on time. Be here by 10:40, and we'll hear from our biologists and see what they think of no fish in Tim's models.
All right, we're going to get started again. I think most people are here. Okay, so now we're going to talk about biology. And so we have two speakers again, one observation, one modeling. And so we start with Colleen Durkin from MBARI to talk about observations.
All right, thanks for inviting me. I just want to start by first acknowledging someone I added as my co-author of this talk, Chrissy Hufford, my colleague at MBARI, because she helped me put a lot of these slides together. So I just wanted to start, I just threw some random videos together showing you a whole bunch of different types of ways that we observe biology, both in the surface ocean and in the deep ocean. I'm going to be talking about that today. And I'll let it go to the end so you get to see all the cool videos. Blue water diving. There's one more cool one after this. Deep sea floats, imaging floats. This one is actually a float in development by Melissa Omond at University of Rhode Island. All right, so I was tasked with giving an overview of biology in just 20 minutes, which sounds really easy. Forward. So I think I just want to make a few points that you'll remember from this talk. The first one is that biology in the deep is tightly linked to the surface, and this isn't something that was always appreciated. And so the consequence of that is that the deep sea biology is always changing. It's very dynamic, and I'm going to show you some examples of that. This is really tall. Okay. The second thing is that, really basic biology in the deep is really difficult to study. And I'll show you examples of that as well. But the result of that is that ecology, biogeochemical roles, and the responses of these organisms are largely unknown. And then finally, something that I think is really interesting that is that the tools we choose to make these observations really influence our perceptions of what is important. And throughout the talk, I'll show you all different types of ways of observing the deep sea. And what this means is that we're probably overlooking a lot of important processes in organisms, depending on how what lens we're using to look at the deep sea organisms. Okay. So first of all, biology in the deep is tightly linked to the surface. And the main mechanism that's driving this link is these sinking particles. And we've already heard a bit about the biological pump. And tomorrow we're going to hear more about the biological pump as well. So I'm not going to talk a lot about those processes, but we are going to have to talk about these particles because this is really what's linking the surface and the deep. And so the biological pump, the formation of these particles starts in the surface ocean with phytoplankton. Phytoplankton are fixing that carbon as they grow. They generate most of the organic carbon that's eventually feeding all of those deep sea animals. And what we're looking at here is a 20-year time series of ocean color, and this is total chlorophyll. And so what we're looking at is total chlorophyll, but not all of this production ends up into the deep sea, as we know, as we saw in some slides earlier. And so we can have some questions like which phytoplankton are most linked to particle export in the deep sea? And until recently, this would have been a really difficult question to answer, but I'm really excited about new developments. So just recently, the PACE satellite was launched. And this has a hyperspectral imager on there. And so it's going to see all the colors of the ocean, and that will allow us to resolve which phytoplankton groups are growing in the ocean. And so this is one of the first light images. What you can see on the left slice of this is South Africa. And the left slice shows you the true color of the ocean. The right is that total chlorophyll, like what I was just showing you in the last slide. And then the middle slice is from that hyperspectral data product. And so now we can start to resolve, okay, near the coast, that bloom was pico-eukaryotes. Offshore is more Senecacoccus. And so this type of biological resolution is going to help us tease apart which types of production are really driving the biological pump and driving that link to the deep sea. So just now we can move beyond into more questions. When and where does phytoplankton growth affect deep sea ecosystems? And is export from the surface to the deep changing? And so to try to get at some of those questions, I'm going to give you an example from Station M, which is a long-term deep sea time series that was started by Ken Smith in 1989, and it recently ended when he retired last year. And so we have 30 years of biological data from the deep sea offshore of California, 4,000 meters deep. And so I'll just show you what that looks like. This is an ROV dive down at Station M from the surface to the deep. So we can see all these pyrosomes at about 60 meters. These are gelatinous zooplankton. Getting down to 1,800 meters, there's still a lot of particles, and you can see some copepods. And I'll just want to point out that, you know, there's things other than copepods down here. I think we'll see like a larvation there on the right flying by. So we often think of the deep sea as not having a lot in it, but there's a lot in those waters in between. And then we get to the seafloor, and there's a pyrosome sitting there on the seafloor. So this is just a pretty obvious example of that link. Those pyrosomes, when they die, they sink pretty quickly. But then there's all that brown stuff on the seafloor. That's those particles that are sinking as well. So the Station M time series had a lot of different ways of measuring biology in the deep sea. So first of all, there was the satellites. I wish I had a pointer, but do I? No. So there's the satellites that measure the production in the surface ocean. Like I showed you before, there was this deep sea rover, the top middle, that measured the benthic rover, which measured oxygen consumption in the sediments, so respiration. Once or twice a year, a ship would go and they'd do ROV surveys of the organisms on the seafloor. They had sediment traps, time series sediment traps, that's the bottom left, measuring particulate carbon export all year, every year, almost every year. Then they developed some innovative new imaging sediment traps that could measure that at higher resolution. That's the middle bottom. And then there was also time-lapse images of seafloor animals on a tripod. That's the bottom right. So in the beginning of this time series, the first 15 years or so, the food supply was lower than demand, and that was calculated by comparing the carbon export measured in the sediment traps versus the respiration in the sediments on the seafloor. And during that time, ecological changes correlated well with the climate conditions. So seasonal variability, El Nino, Southern Oscillation, these types of longer term variations, you could see them mirrored pretty well with animals on the seafloor, their population levels. But then things started to change. This is the time series of carbon export from those sediment traps. So on the y-axis is POC flux, and then the x-axis is over the 30-year time series. And you can see that there's a seasonal variability here, but in the second half of the time series, we start to get an increase in total carbon export, and that's driven by these episodic high flux events. And they just became more frequent and higher magnitude over time. And so this is what that would look like. So these are sediment trap cups, and you just suddenly have this like boom, big pulse event. And so for some animals, this was not a good thing. This is an example of this is the time-lapse images of the seafloor. This is a deep sea sponge. So you see it, if you look at it, it's kind of like coughing. See that white bell shaped? That's the sponge. It's kind of like contracting. And so animals like that don't like a lot of particles coming down all of a sudden. They don't thrive. So in this case, there's a lot of food, but this isn't the type of delivery that is beneficial to those organisms. But other organisms seem to do really well. So here's a time-lapse image of the seafloor. Those red things crawling around are holothurians, like I believe that's a type of cucumber. But suddenly you see this see how the seafloor is getting brown? That's all the particles falling down. And so you just see this flurry of those holothurians, and their populations do really well with that increased food supply. And so if we try to compare this to the satellites at the surface, that red line is the POC flux modeled from the Martin curve. That's based on the carbon export modeled from satellite chlorophyll, and then apply the Martin curve, which is a way, basically just exponential decay of flux. And so what's pretty cool actually is that red line overlaps with the mean black line pretty well, but importantly, it pretty much misses all of those high flux events, which can be most of the carbon delivery to the seafloor in a year. So it's kind of missing some of the most important things, and it's definitely missing the long-term change. And so so now we're looking at this. This is probably my favorite satellite image of chlorophyll off of the California coast. We can see that from that data, the production detected at the surface is not consistently matching the food supply arriving at the seafloor. Sometimes there's really high production at the surface and we don't see anything delivered to the seafloor. Sometimes we see a lot arriving at the seafloor, but we can't quite match it to any event at the surface. And so obviously, one of those reasons could be physics. We have this point measurement on the seafloor and a lot of dynamics in the surface. So I'm sure we'll talk more about that with the physicists, but there's also a lot of other complicated things going on. There are organisms that live in the mesopelagic, so there's a lot of distance between 0 and 4,000 meters, and a lot of animals that live there. So they're transforming those particles as they sink. And then there's also organisms that live on the particles themselves and affect how much gets down. So I'm going to talk about those two things really briefly. So animals and protists live in the mesopelagic, and they intercept and repackage sinking particles. But I want to emphasize that their biology is really difficult to study. Not everything is a copepod. Maybe that's also that's a big takeaway. A lot of the things that live in the deep ocean are really delicate. They're adapted to living at high pressure. They're really hard to see, they're hard to sample, and we don't know very much about them. And so really basic questions like, where do they live? How fast do they grow? How do they reproduce? What do they eat? How much do they eat? Who eats them? How much carbon do they contain? How fast do they sink? how frequently do they produce fecal pellets? How fast do their fecal pellets sink? We don't know these things about most things that live in the mesopelagic or on the seafloor. I'm just going to show you one example of one of these things. This is highlighting work by Natalia Yopez Manfrer. And what you're looking at here is deep sea phaeodarian. It's hard to see. It looks a lot like all the marine snow. If we zoom in on it, this is a colony of protists that produce silica shells, and each of those glowing white things is a cell growing in a colony of silica structure. You can see the marine snow like hanging off of it. So it's collecting, it puts these threads out, collects particles, and then that's what it's going to be eating. And then it eats all those sinking particles, repackages them into these little dense fecal pellets, which then also sink after they're released. These things we don't really know much about these. If you look carefully, you can see this kind of like bubble around it. It's very delicate. Usually if you collect these in a net tow, they're completely destroyed. They don't look anything like this. I'll show you how we collect them with the ROV. We can collect them really delicately and learn a lot about them, but nobody has been able to keep these things alive, including us, including the Monterey Bay Aquarium. They're adapted to living in high pressures, very specific chemistry. And I'm just showing you this example of this organism. This is pretty much true for most of the organisms in the deep sea. But I'm pretty excited about new technologies that are allowing us to learn a lot more. So for example, there's huge proliferation of imaging instruments, and that's increasing our ability to resolve the basic biology of delicate, deep, and unculturable organisms that mediate the link between the surface and the deep. And this is one example from the UVP from Biard and Oman. And then, so this is showing just a whole diversity of these types of phaeodarians and radiolarians that live in the deep sea. And then there's other imaging. I'm just showing you this for fun. This is an ISIS imager. It's a shadow graph imager. And those can also image those. And like, this is what that phaeodarian looks like in the ISIS, which I'm kind of just showing you because it's cool. Okay, so there's all these organisms that live in the mesopelagic, but then there's also organisms that live on the particles themselves that are transforming those particles, respiring them as they're sinking. So the biology on the particles affects coupling between the surface production and the deep sea food supply. The particles themselves are incredibly diverse. So this is just a variety of different types of particles. They're produced by, let's see, what did I write here? They have diverse sources, different shapes, different carbon content, and different sinking speeds. And they're also a hot spot of microbial activity, diversity, and remineralization. And so I'm just going to show you one example of a really cool way to resolve those. And I'm going to highlight salp fecal pellets specifically here. This is a study recently published by Brandon Stevens, where he analyzed the microbial community on individually isolated salp fecal pellets. What we're looking at here, this is a 18S DNA sequencing, so the bacterial community composition on these particles. Every bar here represents an individual fecal pellet. The top set of bars were freshly isolated from salps, and then the next set are isolated from sediment traps at different depths in the ocean. And so 95 meters, 195, 300, and 500 meters. And then the different colored bars represent different types of bacteria, different species, I guess, that are living on those fecal pellets collected at different depths. And so what I want you to see is those freshly isolated fecal pellets that just came out of the butt of a salp, if they have a butt. You know, you see that light blue color. They immediately get colonized by Vibrio bacteria. They seem to be the first responders. They're like, oh, fresh POC, I'm on it. As those fecal pellets start to sink, now you start to see the takeover of that dark blue Those are pseudo-ultramonas. I'm not really a bacteria expert, but I'm told that these are like the weeds of the ocean. I am pretty sure if it smells bad, it probably has pseudo-ultramonas growing in it. They're just really good at taking over on organic matter and breaking them down. And then when we get to the even deeper samples, 300 meters and below, then it takes over the orange bacteria, the Moritella, and those are actually adapted to higher pressure, living in higher pressures. So not all bacteria can grow at all pressures. So some are going to be more competitive at those high pressure as you get deeper. And so the DNA sequencing of individually isolated particles resolves biological dynamics of carbon flux and attenuation. And so I think it's important to at least appreciate that, you know, respiration isn't just this static process as particles are sinking. There's a lot of dynamics happening on these particles, and it might be hard to capture that in a model. I am done early, and so just to reiterate the main points that I want you to remember is that biology in the deep is tightly linked to the surface. Basic biology is really difficult to study in the deep, and the tools we choose to make observations influence our perceptions of what's important. All right, thank you.
All right, so up next we have Daniele Bianchi from UCLA talking about modeling.
All right. Yeah, thank you for inviting me to this wonderful meeting. I'm not a biologist, but I'm tasked to talk about biological modeling. So if you think modeling physics is hard, imagine modeling squishy things that move around and have all the diversity of behavior that we just saw. So that's the starting point here. All right, so I'm gonna quickly give an overview of what I think are the biological connections between the surface and the deep ocean. And this is essentially our good old biological pump. So I'm going to talk a little bit about export and transfer efficiency. And then how do we model these biological pump processes today in the models that we use to project climate change. I'm going to talk a little bit about particles and microbial dynamic. We saw a little bit how diverse that can be on particles. And then I'm going to get into more biological processes where animals start moving around and transporting carbon, so vertical migrations. And since we heard already that fish are not included in models we heard that from Tim, and I'm going to make a case that we should start thinking about fish for many reasons. All right, so here's our starting point, and old schematic of the biological pump, which I think is very, still very actual, still very useful, except that now what we care about that is happening a lot below the limit of this, or the limit of this diagram. So biological pump is part of our carbon sequestration, oxygen loss in the deep ocean, and also fuels deep metabolism. A lot of the dynamics here is dynamics of large aggregates that sink fast. So that's a quick connection. In a matter of days, some of these aggregates can sink kilometers. And what happens to these aggregates as they sink is important. So aggregation, formation of particles, maybe because of those zooplanktons, and fragmentation matter a lot for how this material degrades in the deep ocean and what microbial communities do. But of course, there is another rapid connection, which is animal moving up and down the water column. When this diagram was put together, it was mostly zooplankton, but today we know enormous biomass of mesopelagic fish goes up and down day and night. They are followed by large predators, and potentially this can affect the biological pump. All of these processes can be altered by climate change, but I would argue that there is another perturbation to these processes, that is the global fishery. So towards the end, I'm going to think a little bit how we can incorporate another, call it stress or call it perturbation, which is the fisheries. They might affect all of these side of things, but potentially the connection go to the biological pump. All right, so in terms of export, we like to think of particles starting at the surface, organic material sinking, maybe being transported by animals. A lot of attention went to the surface, net primary production, and how much material is exported. But really, we want to start understanding how much makes it to the deep ocean, how much is respired, how much sink. When you see a respiration, you multiply that by a time scale, and you get a carbon sequestration, and potentially you can get an oxygen utilization as well. So in general, we know quite more about export, but what we want to know more about is the transfer efficiency. What's the flux at any depth in the deep ocean relative to what is exported at the surface? Maybe this can be down to 1,000 of meters. In general, a lot of attention has gone to the mesopelagic zone transfer efficiency. So something between 100 and 1,000 meters, but again, we can go deeper if we have observations to constrain these quantities. So how much do we know about particle export? Still observational estimates are very uncertain. Andrea made a point about primary production being uncertain. That propagates into export with more sources of uncertainty. So these are two satellite-based, sort of a data fusion of in situ data that provides algorithms to propagate export from the surface to the interior, ranging from 3 to 10 petagram of carbon per year of particles sinking out of the surface. These are a little more recent. This is from Team Devries and Weber. So the Monique et al. Paper that is showed is kind of an evolution of this, and this is a similar hybrid empirical mechanistic model. So large uncertainty. These are observational estimates. They are models that cook satellite data and in situ measurements, but they're still, I would say, they're still models. What about mechanistic models that we use to project climate change? So there is a very nice review by Adrian Bird on modeling export. Each one of these lines is a global Earth system model from the CMIP6 experiment showing carbon export fluxes in petagram per year. I don't remember if it's just particles or everything. I think it might just be particles. But you can see a huge range. They also go further in time, so you can see a potential effect of climate change. I guess the point is that the uncertainty is as large as we have in the observation estimate, so same range of uncertainty, more or less, or even more. It's interesting that going into the future, all these models projected decline export, so that is going to be something that changes the deep ecosystems. I would say that there are some interesting, not all at the same rate, some even have a slight increase in export, even though the consensus seems to be a decrease, which might have to do with stratification. But I would argue that this is not settled. We should think about what happens in the future. And there are multiple sources of uncertainty, and many of them are biological. There is a review paper that recently came out by Stephanie Hanson et al. That look at different biological processes and also physical, but here I'm just highlighting the biological processes that are represented in models or maybe not represented but might be important. So many are poorly represented in CMIP6 models. So if you take, I don't know, your favorite one, zooplankton vertical migration, that might be my favorite one. Of the models that they look at, 0 represent this pathway. Fish vertical migration, also 0. Many have microbial processes. So you can have fun looking at your favorite process here. The point that they make is that these are a source of uncertainty today and a source of uncertainty in the future. If you see a question mark, they argue that we don't know what the effect of including or excluding this process is for present day or future projections. And the dynamics involve microbes, so things like temperature-dependent remerization of particles or oxygen-dependent respiration. This might be microbial, might also be metazoans, and some are directly related to zooplankton and fish, so all biological processes. And all of these influence the transfer efficiency, how much carbon is respired in the mesopelagic zone, how much makes it to the deep ocean. If export is uncertain, transfer efficiency is even more uncertain because all of these processes are poorly represented in models, and that reflects a sort of poor understanding and the lack of global scale data to constrain these models. So I look up some of the recent estimates of transfer efficiency. Again, this is how much carbon makes it to 1,000 meters relative to 100-meter depths. This is for different regions. Is a sort of model database fusion by Cram et al. It goes anywhere, depending on the region, from a few percent of the carbon surviving at 1,000 meters to 20%. Now, the interesting thing here is that they use the mechanistic model, so they can tell us what processes seem to be important in this model. And in order of importance, they argue that resolving the size spectrum of particles, large versus medium versus small particles, is important, is the process that had the most influence in their model as they constrain with the data. The second one was temperature-dependent respiration, so how microbes might crank up their metabolism at higher temperature. Oxygen dependence. Turns out that in oxygen minimum zones, a lot of organic matter escapes to the deep ocean, so you see a great improvement in the Eastern Tropical Pacific, where it's low oxygen once you add that oxygen dependence. And finally, mineral ballast, which is something many models include, but I think once you start resolving size spectrum, it's unclear if it's large particle or dense particles that matters the most. This is what they get from this exercise. So red region is where you get a quick connection between the surface and the interior, so a lot of the material makes it deep. And the blue regions in the subtropics where this transfer is lower. But I would say this is just one of the estimates, and the uncertainty there is as large as the export or even larger. Why does this matter? So this matters for projections of export and potentially primary production. So this is a study by Keith Rogers and al. That I'm involved, and it should be coming out in the next few weeks. So we look at primary production going in the very far future, 2300. There is an enormous structural uncertainty in CMIP6 models. We basically can go from a reduction of primary production to an increase of primary production. And it turns out the argument that we make in this paper, and it might be an oversimplification, is that the way you remineralize with temperature, the way the temperature controls remineralization matters. So in a model like the IPSL model, you have temperature-dependent remineralization. You have nutrient trapping going into the future in the thermocline. Nutrients are maintained close to the surface and can fuel some primary production going into the future in a way that in this model even increases. Other models that show a decrease actually trap the nutrients in the Southern Ocean, and many of these models do not have temperature-dependent remineralization. So the way you model this process might be really part of the structural uncertainty that we want to reduce. So I've been talking about processes that happen at the scales of particle potentially. I'm really excited about work that is coming up where this is from Naomi Levin's group at USC, is a postdoc there that developed an explicit models of particle microbial interactions that is quite complex, resolves microbes attaching and detaching and growing on particles, the free living fraction. And the point is not throwing complexity just for the sake of well, it's interesting, let's do it, but also because transfer efficiency might be an emerging property of all these dynamics. And so with complex model, we can maybe backtrack useful parameterization for the global model. So I'm really excited to see this type of efforts in the future. For the next part, I don't know how much time I have. Oh, there it is. I'm going to focus a little bit on thank you. Great. Focus a little bit on animals and start with vertical migrations. So we already saw Tim talk about that. So at night you have zooplankton tend to be close to the surface. They can feed. It's dark. Predators have a hard time seeing them. And during the day they swim deeper in the water column to escape these visual predators. By doing that, they transfer organic matter. They also produce fecal pellets at depth. Maybe some of them die and sink to the bottom of the ocean. They interact with oxygen and carbon. How can you model that? So in my more than 10 years ago with Charlie Stock and other folks at DFDL, we couple a model of DL vertical migration, really an explicit model, to a NPZD model, typical of what global models do. And we really wanted to try to model mechanistically DL vertical migration, but also think about the trade-offs that these organisms have to undergo. what controls the processes, and what are the impacts on the biological pumps. Every time you see this red squiggly line moving up and down, these are migrators that follow a certain light level in the water column, but they have all the interaction. They feed, they excrete, they produce particles, and you can analyze this output. And what we learn is that there is a potential for zooplankton, shown here in red, relative to sinking organic particles in green, to really contribute a lot to respiration at the depths where they migrate. These are fairly well constrained. I'm going to show you a slide in a minute on that. And so at these depths, with the model, we can start disentangling how much is local respiration, how much is particle production, and other processes. And so the idea is that at certain layers in the mesopelagic zone, migrators might be really important for the biogeochemistry. This can be parameterized. So to parameterize this process in a global model, you need some observation to constrain this behavior. We're talking really about behavior of animals that are extremely diverse, so we need simplifying assumption. So another study that we did was looking at acoustic data that tell us where in the water column these migrations happen, and this is just a fraction of the migration. But what we learned is that they vary a lot in depth. They are shallow, where there is high chlorophyll, sort of dark waters or low oxygen, and they go deeper than several hundred meters in subtropical gyres. So you can try to use some of these observations to constrain the behavior in models. We did that in an early study in 2013, where we look at the impact of this migration on oxygen. And what we learned there is that in some parts of the ocean, in the thermocline and mesopelagic zone, animals might be really important to kick oxygen to low concentration. These are very close to oxygen minimum zone, so we think there might be an influence. Oxygen utilization is also, if you think about that, is a synonym of carbon sequestration, so these animals also sequester carbon there. And I would say that today there are only a few global models that have some form of DL vertical migration, and some examples were provided by Tim. Actually, Tim's model is one of these. Olivier Aumont in France has also coupled a nervous system model with DL vertical migration and used that. So still a lot of work to do there. For the last part, 5 minutes, we're going to talk about a little bit about larger organisms that are even less well constrained than zooplankton and particles. So fish and fisheries. I've been working trying to do projections of fisheries and climate change, but at some point I was trying to connect that also to the biological pump. And so one thing that we did in a paper that came out a few years ago was trying to estimate what's the fish biomass. And this is only commercial fish, so fish that are exploited, and is a model-based estimate. And I say commercial because we have observation for a lot of commercial fish. We don't know what all the fish in the ocean are. You would think it's something scientists should know, but it turns out I wrote an entire paper on that, saying that there is an enormous uncertainty there. And also, I was curious to start thinking about the biological pump effect. And so try to estimate how much of particles can be produced by this standing stock of fish, and what's the fate of particles once they are entering the deep ocean. And so if you think about slowly sinking particles, you can describe them fairly well with the Martin curve that was also introduced earlier. And so maybe start at the surface, most of the flux is in these slow sinking particles. And then you add particles that sink quite rapidly. Fish fecal pellet can go kilometers every day. And so if you make them 10 times faster or so, you get almost like a straight flux where most of it makes it to the deep ocean. Some of it will be respired even in the sediment. And so it turns out that by the time you get to the deep ocean, if you start with only 2% of fish particles, fast sinking particles, you can get to maybe something like 10% of those make it to the deep ocean. So it can be important for deep ocean biogeochemistry. We try to estimate that, coupling this export to an estimate of the residence time of water from an ocean inverse circulation model. So I look at oxygen utilization caused by those fast sinking particles. units are percent of all the oxygen utilization that you see in the deep ocean. So if you see red colors, this is the signature of those fast sinking particles that might be produced by fish that get remineralized in the deep ocean. It can be up to maybe 15% of all the oxygen utilization we see in the deep ocean, and potentially the carbon sequestration that go together with that. So in the paper, we estimate about 100 petagram of carbon sequestered by these fast sinking fecal pellets. I'm really excited about some work that kind of expanded this type of thinking. So this is a paper by Jerome Panty, who's somewhere in the room. It's an amazing paper. They essentially take a massive functional type approach to model the vertical migration and food webs. And they are able to estimate the carbon sequestration that they can attribute to different animal groups. And anything that is bluish to green to yellow, not the super yellow, is fish. So these are really carbon sequestration attached to fish. And if you have questions, please go to their own, because it's probably much more accurate than anything I would say. But to me, reading these papers, that fish have a surprisingly important role, according to this analysis. This is because of deep injection by migration, but also the formation of these fast sinking particles that can make it to the deep ocean. They estimate about 3 petagram per year total, but a chunk of that is fish and a large sequestration. And again, you can look at your favorite group and think about how much sequestration might be attributed to those animals. And again, these are processes that are not included, or maybe they are heavily parameterized in models. Things change over time, so I'm gonna go quickly through that. There are projections of phytoplankton decline, also projection of zooplankton. So the interesting thing is that zooplankton seem to be declining faster in the future, according to our best models. This is what we call trophic amplification of biomass decline, is well explained by a paper by Lester Kwiatkowski. And you can extend that to fish. So we have fisheries projections that suggest an even larger amplification of this biomass decline. I would say this is extremely uncertain, so don't take it with a grain of salt. So I'm gonna finish saying that there might be interaction between fisheries and carbon cycle that we are not thinking much about. They have been the focus of a couple of papers by Emma Cavan et al. So you can alter the carbon cycle by all sorts of fisheries processes. Where do these overlap occur? You can use models and observation to start mapping out where you might expect some overlap between fishing activities and the carbon cycle. And this is a paper in review by Mariani et al. That looks at where there is high sequestration and export and high fisheries, or both. These are all regions where maybe fisheries are impacting the carbon cycle. So I'm gonna stop there. Maybe just a plug for the FishMeep project, which is a sort of collective development and evaluation of fisheries models. So it's an amazing resource that I encourage you to look at. And I'm gonna stop maybe with a summary, but I don't need to reread it. So thank you.
Questions, and Colleen, if you want to come up too, with opportunity for questions for both of our panelists. And coming in hot, we got Gokhan.
Thank you. So maybe one clarification question and another question. So what is the, when you guys say fast and slow, what are we talking about? How fast and how slow things are? And how do you tag the bottom stuff? And how do you, I guess, connect the bottom stuff to a particular surface location? Because that was implied, I believe.
Yeah, fast and slow is a continuum of sinking speeds. You can imagine small particles might sink a few meters per day or even be suspended, and the large fecal pellets might sink kilometers per day.
What is the kilometer? Okay.
Kilometers per day.
Per day, okay.
And so there is that's why I'm excited about thinking about the size spectrum of particles, which is something you can start observing with the UVP instruments and other optical instruments quite completely. So there's really a spectrum of particles. And in models, we usually either have one size class that sinks at maybe 50 meters per day, or a couple of size classes slowly sinking, and again, like several tens of meters per day. But the fast sinking fecal pellets are kilometers per day. These are observations from Grace Saba and other folks that see them.
Okay.
if you were asking about the connection between the deep and the surface, if you're referring to that station M link.
Yeah.
So I believe the way that was done, I mean, it's just a statistical, I don't remember how big the circle is. They looked at the satellite images from a circle over Station M and assumed, and just did the statistical connection there. But there have been studies doing particle tracking, like reverse particle tracking. And those have shown, or I can think of one, that the particles could potentially be coming from really far away, depending on how fast they're sinking. So that's why it's so hard to make that direct connection. And probably that's why, those high flux events is like, where are they coming from? I mean, I don't know, probably from the coast somewhere, but yeah, could be far away.
So thank you very much both for your very interesting talks. I have a question for Daniele. I was wondering how much is important the vertical resolution of the physical model in solving the vertical migration? Because as a physical oceanographer, I know that vertical resolution is very important for mixing whatever. And so I would be curious to know how much is important also for the vertical migration. With an higher resolution, the process is better resolved. It's just your comments. It's not, don't expect an answer.
I think most model resolution today could resolve the main layers. The uncertainty is so large that I don't think you need to go to very fine scales. There might be issues with the way you sort of time step the model if things really sink many layers per time step, but that's more of a technical issue. I would say for the process, I don't know if we really know, but I would say models should be able to capture the main layering and vertical gradients in degradation and migrations, I hope.
Yeah, a question over here.
Question for Colleen. Great talk, like your video. So I think I'm wondering about, in terms of respiration, how important is the in-water respiration in the deep ocean versus benthic, because they have more like a time spending in sediments. How, like those two processes, do we understand the right importance in terms of how they influence the deep sea biogeochemistry, nutrient cycling?
I don't think I can answer that question, but I was thinking about that too with your talk about the delivery of the fecal pellets. A lot of them are landing on the sea floor and not being respired in the water. Probably a lot of them are actually landing there and being respired by bacteria on the seafloor or eaten by all those animals. I mean, there's actually a lot of animals on the seafloor that are eating them too. And then some of that gets buried, some of it ends up in the bottom water. And then I was kind of thinking about, like, did those models incorporate that respiration like on the seafloor, or is it, or just burial? Yeah. I don't know. I answer your question with a question.
For the models, I think there is a current effort, and I think Christine and Charlie are people to ask, to really expand the representation of benthic sediment water column coupling and what are the dynamics there and exactly this type of interaction. So I would say that's one of the, again, like the frontiers of modeling, and it might matter for all the reasons we've learned.
Thank you.
Yeah, one in the back.
Yeah, thanks for the talks. I have a question for Daniele. Could you talk a bit about how all these different variables are actually represented in the models? Like, is POC a concentration that also gets advected around and then it also has this sinking flux? Or is it like in a vertical column, there's just the sinking flux? And the related question is, how many tracers are there in these kinds of models that now have fish and everything? And how much does that slow them down?
There are no established practices in something like the bathymetry of the model, so it may be for particles. There is even less established practices, I would say. But so some models represent particulate organic carbon as a pool, as a concentration of carbon, nitrogen, and other elements that is advected and sinks and produced and transformed. Some other have just a representation of the flux, so maybe instantaneous redistribution in the water column. As soon as you add processes and tracers, you increase the computational complexity and the sort of parameter space that is hard to constrain with observation. So even if you start having a size spectrum of multiple particle sizes that are sink and advected and produced, how do you constrain that? What observations do you use? And today we're quite limited. So it's both a computational and a sort of observational limitations. It's an ever-evolving field. I would say, to me, the frontiers is having multiple size classes, if not a full spectrum, and think about even the lateral attraction and the interaction with the circulation, even at higher resolution, especially for regional scales. Maybe.
Thanks. So I think this question's for Colleen, but Daniele may also be able to partially answer it. The ecologist in me gets really excited about this microbial succession that we see on sinking particles, and Colleen showed it on the salp fecal pellets. And so we see this rapid succession, but the biogeochemist in me says, well, these salp fecal pellets are sinking so fast, hundreds, even maybe kilometers per day. How fast is that occurring? How fast must these organisms be growing? Is there time for them to do respiration, or are they really getting all their carbon to the deep floor? I'm wrestling with that.
I should be able to answer that, but I don't remember from the paper. But I do know one exciting thing in that paper was that model that I can't Nguyen came out of Naomi Levine's lab. They were a collaborator on that, and we're able to apply that model to these pellets as well and recreate that same type of succession. So I bet from that you could probably get out the rates, the growth rates and respiration rates.
But it's really amazing to see this succession. That means that there is enough time for the community to build up and change over the sinking time scale, which has to be days. So it's fast. I ramble along with this question, but I tend to think that some of these fecal pellets, first of all, they come out already colonized by a lot of, it's very juicy, fresh material. ELISA dreads have electrode measurements that show that they go anoxic as soon as you get in a millimeter into the particle. So there is a lot of respiration happening, but how does that change with depth? What are the metabolisms involved? I tend to think a fecal pellet is always in equilibrium with the water. It takes a few minutes to equilibrate diffusively. So it's really what the microbial community is doing and how quick the organic material is being utilized that kind of controls that succession and the tapping to the water column.
Thanks.
And this will be our last question, because then we're going to have all the speakers come up and sit here for a panel discussion.
Okay, this might be a bit of a naive question because I'm a physical oceanographer, so bear with me. In terms of the fish potentially contributing so much, is that like in large part related to just the size of the pellets being larger? And so like as they're sinking and being respired and some of that might be dissolving, like there's just going to be more of that pellet left by the time it gets to the bottom versus the zooplankton one? Is that a good way to think about this?
Yes, by the time you get to the deep ocean, large, fast sinking particles are really preferentially delivered to those depths.
Thanks.
Great. One more round for our biologists. Two in-house speakers, if you want to come on down, and then we have our two virtual speakers. Hopefully they're still online. So what we're going to do for the next 30 minutes leading up to lunch is this is kind of the opportunity to, so far we've stayed in our silos by discipline, by observing or modeling. And so this time of the discussion is to start breaking down those silos and finding some cross-pollination between them. And so just any thoughts you guys have, any questions you guys have, particularly as we cross-link across things. So yeah, to kick us off, and do we have an extra mic that we can run around? All right, well, go ahead and shout.
Start to define what deep means, like in this workshop, like a little bit more.
Oh!
I mean, now we have biologists, chemists, physical oceanographers, just like, yeah.
As long as we all agree that we don't need to come to an agreement, go down the line and each of you say what in your heart of hearts you feel deep is.
Start with Daniele.
Oh, well, I mean, the scientist answer is it really depends on your question, but my preference, I say deep is anything below the euphotic zone. Abyssal is anything below the mesopelagic zone, but I will not tell you depth layers.
I would agree with that, but I would also, I kind of wonder if we really need to define it in the context of this workshop, if the point is to find the links between the surface and the deep. It's all linked, so kind of, I think it doesn't matter.
I mean, from the physical side, I would define it the upper ocean, deep ocean, and abyssal, so 3 layers. Upper would be pretty much where the mixed layer depths or boundary layer depths are, and that can vary from a few hundred meters to a few thousand meters, depending upon the location. Below that is the deep ocean, and then I would say below maybe 4,000 or 5,000 meters, I would call it abyssal ocean.
Yeah, I think I agree with that, and I think for the deep ocean, it's essentially beyond the max winter mixing in my perspective, like where you're not routinely exchanging with the surface outside of deep water formation regions.
All right, Tim?
What is the deep ocean? Maybe below the like wind-driven circulation. So you might have like mixed layer, and then you have kind of like thermocline, and then below that is the deep ocean, I suppose. That's one answer.
And Sarah.
Yeah, I think I agree with what's been said on the physical side, which is below the thermocline is kind of the deep ocean, and think more about the water masses. So, I mean, in the physical sense, we tend to think about the deep ocean as, you know, below 1,000 meters to 3,000 or 4,000 meters, and the abyssal is kind of below 4,000 meters.
And I think something that we should all consider when we think about this question extends beyond this. It's the fact that we're all from so many different disciplines. And so make sure when we're having conversations to take a moment, if you don't understand a piece of vocabulary, it's just because it's not part of your discipline's lexicon. So let's all just be really good about asking what that means and then explaining what it means so that we can help share our knowledge with each other. And so if there's a point of confusion, it might just be because you guys are talking about 2 different things using the same words, or the same thing using 2 different words. So I think this is a really good opportunity for that. I have a question for Sarah and Gokhan. So I was thinking about your cross sections about the Antarctic bottom water and the North Atlantic deep water. And you guys both had different cross sections that you were showing at different times. And they didn't look the same. So how do we get them to look the same? Kind of understanding that models need to be advanced in such a way that they're representative of the real world, but maybe also our real world sampling, because of its sparseness, isn't showing all the bits and bobs. So what do you guys think? How do we get your maps to look the same?
Sarah, do you want to take that first, and I'll...
I guess, so you're asking the same between the modeling world and the observational world?
Yeah, I was just thinking Gokhan was talking about, when we did X, Y, and Z with the model, Antarctic bottom water just filled up the whole ocean. And in your map, it was very clearly that was not the observational data. So how do we merge that together, observational data and modeling data, to make both better? Like, what's the missing piece to do that?
I mean, I think it's kind of what we're doing now, which is we need to understand the processes that kind of set those bottom properties. And I think that the lesson learned here is that it's really sensitive. You can change the mixing by a very small amount, or you can change the ventilation or just the surface forcing by a small amount, and it's going to have big impacts on the MOC, which is going to set the interior ocean properties that you see in those various models. And so, yeah, I think it is sensitive. And so we have to understand kind of the smallest scale to the largest scale to get it right is the lessons that we've learned.
And then, yeah, I mean, I agree. And then I would also add that we need to make sure that we are comparing apples to apples.
Mm-hmm.
In many comparisons with the observations and models, we tend to not do that. And I mean, as Mike knows, from the Atlantic side, we have projects looking into comparisons, exact comparisons of, for example, transports at Samba, at Move, at Rapid, at OSNAP, and that's why I say when I trust observations but verify, we are finding actually challenges, issues with observations, because observations actually use models at some point. When you use pressure gradient, right, with the thermal wind, that's a model. And then it depends upon your accuracy of the pressure gradient measurements and what the reference depth assumptions are. So I think in these comparisons, we need to be really careful as to what we are really comparing, what the observations are measuring, the underlying assumptions. And that's a tedious task. And I mean, we are trying to do it in AMOC community and it's taking so much time. And I think we need to do it in other fields as well, just to make sure that everything is actually in line.
Yeah. Well, and just thinking about Sarah's map about Antarctic bottom water has different biogeochemical properties in it than the North Atlantic water. Then I start daydreaming, well, if we just throw a bunch of BGC Argos in there, then could those be used to trace the source water? Sorry, I'm dominating the conversation. Anyone have any things in the room? Go ahead, Charles.
So this morning it really got me thinking about the sequestration flux at 1,000 meters and how we constrain it. It's always something that we struggle with our models. You know, we have point measurements and they always look like they're sort of all over the map, and we have correlations of 0.3 and we declare success. We have biogeochemical tracers that are subject to all the uncertainties in deep water dynamics that we heard about this morning. And then we have maybe benthic fluxes, but I often wonder how much aggressive extrapolation is done to provide those estimates. So I guess my question is, what do we think is the key constraint on that 1,000-meter flux? Is it the particles, the biogeochemistry, that the benthos, some combination or something we haven't done yet? Because I feel like it's a really uncertain piece of the puzzle.
Good question.
I can say something, I guess. I don't know if it's an answer, but I think another way that people are starting to think about going about this is to, as we have larger data sets and can start thinking about basin scale or global scale changes in biogeochemical parameters, we can look at, for example, interior ocean oxygen changes, or if you can reconstruct interior ocean carbon, you can look at changes in that over time. And I think that looking at regenerated carbon changes or AOU changes might be a really valuable way to get away from point measurements and get the bulk chemical signature. But again, that will have its own uncertainties, but might be able to do it at a large scale.
I mean, I would say all of the above that you listed in terms of uncertainties. And I'll see from the modeling point, but I will also imply observations in that sense. I think we keep saying that the models are all over the place, and then you saw, I mean, a bunch of examples of models showing decline or no decline of some inventories and all that stuff. The part that we tend to miss in the modeling community or in the models is that, yes, we get certain things, and yes, we can explain those certain things based on our model equations. And we can say that this process, diffusion is not working, or advection is too weak, or something like that. I think we need to make sure that when we have observations, we need to make sure that we have complementary process-based observations to help the modeling community. So we have observations at 1,000 meters. We can get biogeochemical Argo or maybe deep Argo, but I don't know, I'm just putting it out there. I don't know how to do it myself, essentially. But can we essentially say that temperature is somewhere, is whatever, something degrees Celsius, and salinity is something, and biological concentration is something. But would it be possible to complement that, saying that temperature is this because this process is dominating that temperature flux in that region? Can we get that kind of information from observations? So that then in that case, we can actually push the models so that we can discriminate within the models, saying that, well, if a particular model is getting it for this, then we can perform a budget. It's easy to do in the modeling world. We can determine whether a particular model is doing it for the right reason. If it is wrong, why it's wrong, we can explain it. So that is a marriage of observations and models from all over the place, but I don't know whether it's even doable from the model. I know that like OSNAP is doing to some of those, but I don't know if it's true for everywhere or not.
Tim online, go ahead.
Yes, I was just going to weigh in on what's the key constraint on the flux into the deep ocean. So the key constraint is two. It's one, the oxygen, dissolved oxygen, and then the circulation. So if we know those two, then we basically know the flux into the deep ocean, or at least the respiration of carbon in the deep ocean. So we have to measure dissolved oxygen. So keep going with the BGC Argo. And then to get the circulation, we can't measure that, right? So we need all the tracers that go into those calculations, obviously temperature and salinity, but CFCs and radiocarbon and other tracers that can tell us about the rates of ventilation. Once we have those, then we can get the flux into the deep ocean.
Let me ask a question. How much does it matter what the mechanism is in the model that's driving those changes or the sequestration? Because that seems like that determines what kind of observations you would need to make, if it matters what the mechanism is. And I was thinking specifically about, with the BGC Argo, when it accidentally profiled every day, you might perceive a different mechanism than if you get the seasonal average of the biogeochemical consequence, right? And so I'm wondering how much that matters in a model, what the mechanism is that drives the change.
Well, ideally, if we want to trust the model, we need to make sure that the model is getting the right thing for the right reason. And that's why I would argue that the mechanism matters. But you're also touching upon differences in mechanisms based on different time scales. So the mechanisms could be different on a daily time scale versus a monthly time scale versus a decadal time scale. So I think it's important to understand that to build, we can, I mean, as I showed and many others showed, there are like, I don't know, 30, 40, 50 CMIP models, and they are showing something. So we need to be able to essentially discriminate against some of them. And that's what I'm trying to essentially sort of push to for.
Colleen, you were doing something? My biology brain here, but I guess in some ways the biology doesn't just care about the total integrated flux. It cares about the space-time variation of the flux. So there's two problems hidden in there, right? The problem that Tim was outlining is in many ways, how do we understand the integrated flux over time? But the problem that you're showing in your beautiful videos, Sarah, is that it's not just the integrated flux, it's the timing of it. So there's maybe two sets of observations that would be needed to unpack that.
And maybe, Daniel, can you speak to that with the biological models from that perspective?
Yeah, it's a hard question. I definitely think more flux observations at 1,000 meter will be useful and potentially try to sample that more broadly as we are sampling other biogeochemical variables. It's really hard. Maybe optical instruments can expand that level of observations. And then I will go back to what Tim said, that there are many, many constraints that you can integrate with models. And so that is a very, very powerful approach. And we saw many examples where for the carbon sequestration, you need both the circulation and the export flux. And maybe you can backtrack one from the other. But to have a consistent model, you kind of need the observation of the tracers and the fluxes and sort of do the best that you can. And we know all the degrees of uncertainty there because flux is a reflection of so many different processes and all take a chunk of that. So it's hard, but I would like to see more direct in situ observations of sinking things and creatures.
All right, observationalists, that's your to-do. Sinking things
I like your answer.
or creatures. You have two options. Go ahead.
And maybe this is the same question that you just asked, but I was curious of taking this idea that we need more process level understanding to understand the distributions and the rates. But I was really struck by the figure that you showed, Daniele, about the structural uncertainty in net primary production, and in particular that all the models seem to perform fairly well currently and historically, and it's the future change in temperature that really we can see that the change in temperature dependent remineralization or differences in temperature dependent remineralization makes such a big difference. But how do we know which is right? Like what, and I guess this is for everybody, what are the key observations that we need now to say what should the structural forms of those models be, or what are the key processes or studies that modelers should be doing to disentangle some of those?
Yeah, it's a great question. In a longer talk, I should probably preface that probably those models are not really designed to capture primary production to year 2300, whatever that means. The uncertainties there are huge. And as Gokhan said, we know a lot about the processes that once we put them together, so many things can change. That diverging projections of primary production reflect changes in circulation that alter sea ice around Antarctica, and primary production, of course, and remineralization, nutrient redistribution. Once you go to those long time scales, everything matters, and it can really be pull the models in different directions. So, you know, that's an extreme example of structural uncertainty and the consequences of that. But it's more to highlight the point that the way some of these processes are parameterized will matter more and more and more as we go towards the future. And one of those is this transfer efficient. Where do you remineralize particles, and does that depend on temperature? Is it going to increase in a warmer world or not? So again, models highlight important processes for certain time scales and where we should put some of our energy if those are questions that we care about.
Tim, what about you with biogeochemical models? And I'm just thinking about things like CO2 solubility and all that jazz with a warmer future.
Oh yeah. So I mean, so some I think like we have a good handle on, right? Like the CO2 solubility and its variation with temperature. But I think like the biological parts of the model, we just don't know. I mean, essentially the models, they're just equations and parameters, and we can't really measure the parameters in the real world, but you just can't. So I think the way we need to go about like constraining the models, I guess, is using them to predict things we can measure, and then comparing those to the things we can measure, ocean tracers, for example, or sinking fluxes or things like that, right? So yeah, there is a parameter in most models, which is the temperature dependence of this particular detrital pool in the model. But you just can't measure that in reality because it's just a parameter in the model. It has no analog in reality, really. So that's kind of my 2 cents about it.
Well, Sarah, do you want to comment about what we can measure in reality?
Yeah, I mean, I think in general, it's kind of funny. We had this nice meeting last week from Polar Programs to talk about kind of Southern Ocean observing. And I think, a big thing there is fluxes are really hard to measure versus just measuring the properties. And I guess I would emphasize that I agree that this connection between modelings and observations should be better integrated, and we should be talking to each other more. I think models have the advantage of they have the physics, and you can decompose it and do the budgets really easily and actually look at the processes that are underlying that's driving what we see in the models. And it's much harder to do in observations. But in observations, we can measure a lot of different things. So for example, we can measure temperature and salinity, and that constrains the problem to some extent, but just adding oxygen, adding one more variable tells us a lot more information. And so I think there is value in just the number of variables we can measure in the ocean. And I think they all tell us something useful about the circulation.
Okay, we got Lynn's hand. Oh, we got an online question, and then we'll get Lynn a mic for the next one.
Yes, we have an online question from Jim. Go ahead and unmute Jim.
Thanks. Again, this is Jim from University of Hawaii. I wanted to sort of follow on this idea about the observations. And Gokhan, you mentioned AI in your talk, and that made me think, you know, these deep measurements are incredibly hard to make. And when I'm talking deep, it's, 4,000 meters or so. And it takes a tremendous amount of effort to get the accuracy that you need in order to discern the changes, because they're just so small. And I hope there's somebody in the audience there that's familiar with the Smart Cable project, but that's one effort underway to outfit these trans-basin telecommunication cables with relatively cheap sensors. And so my question is, do you think that if you had widespread geographic coverage of sensors that have somewhat unknown accuracy and drift, could help constrain the models better than a handful of measurements that are known to incredible accuracy? I hope that question makes sense.
No, I think it's really poignant, especially in the context of not just at the seafloor with smart cables, which I'm not surprised a person from Hawaii knows about smart cables where Bruce Howie is located, but also in terms of low-cost technology and getting more cheaper sensors in the water. So yeah, panelists, what do you guys think? Would that be helpful, or would that just be a can of worms?
Just close your eyes and do it.
I think it'll definitely provide additional constraints, but I'm a bit, another possibility, well, there are so many MIPS around, and I'm sure maybe somebody has done this already. Right now, we are talking about physics, biology, ecology, all on an aggregated sense, right? And when we talk about the biases on the biogeochemistry side, and I think, as Charlie indicated, that it can be, or somebody, I can't remember who, well, it can be circulation dependent or something like that. Is there any sort of intercomparison project out there that can essentially constrain, let's say, the model physics side for a bunch of models, but then they can essentially evaluate the biogeochemistry components or fish components in isolation? Or you can be doing the reverse thing possibly, but to me, constraining maybe physics is the easier part, and then just evaluating the BGC part. I don't know whether there's such a MIP in that case. That would evaluate it across multiple models with the same physics. Of course, there are caveats, but then it can evaluate a bunch of BGC parts. Maybe there is a MIP already there in a constraining way, so that might be another path forward.
If not, someone should be writing down this idea very quickly, because this is a good one. Yeah.
If I could just follow up quickly on that, Gokhan, I think part of the issue there is a lot of the available output is mainly for the upper ocean. And, for example, I think if you wanted to look at sub-monthly timescales in the deep ocean, it'd be hard to get that product from a model. I could be wrong on that, but you'd have to run that MIP right from the get-go.
Right, but you don't necessarily have to base it fully on observations. You can essentially create an acceptable physical state, and then that can be constrained, and then check the biogeochemistry against that. So that might be a possibility.
Maybe I can comment on that. I think it's a great idea. It's a lot of work, hard to fund. Yeah. It has been done in the biogeochemical community to some extent. I know, for example, evaluation of one-dimensional ecosystem models done by Margie Frederick, where they fix the physics in 1D. It's easy. You can do a lot of experiments, and they run with 5, 6, 7 different BGC models, and they show a lot of difference. And that's where the models are useful, because they identify those structural uncertainties, and then you can start thinking of what's the underlying cause. Three-dimensional models is much harder because the computation. I think in the UK they did it to decide what biogeochemical model to run. So there is a paper also by Kwiatkowski et al. That pits against one another 3 or 4 UK models with the same physical circulation, with a lot of limitation. Maybe it's not run to equilibrium, very elusive, but it's a very useful exercise, but time consuming.
Tim, go ahead online.
Yeah, I was just gonna weigh in on that question, which I thought was interesting of, is it better to have like a little bit of really high quality data or a lot of maybe lower quality or data with biases and drifts? So I think for sure we need like the really high quality data that we know is true to constrain the models. But I think if you have that, you can throw in a bunch of data that has biases. As long as they're consistent biases, the model could probably learn whatever kind of model it is, inverse model or machine learning model, could probably learn what those biases are if it knew the right answer in certain times and locations. I think the drifts part though is probably bad. You know, especially if you're looking at changes over time. I'm just thinking of like, for example, there were some drifts in some Argo salinity sensors and oxygen sensors, and that really threw off the ability to see what was going on over time. So I think drifts are probably problematic, but lots of data with consistent biases is probably handleable if there is some like really high quality data to back it up.
Nice. And I know we have other questions in the audience, but okay, real quick, we got 1 minute till lunch. All right, Lynn.
I'm a physical oceanographer, so this might be irrelevant, but the BGC floats all have backscatter, so they have FLBBs on them, and we've got 10 years now of data, so we can do the POC down to 1,500 meters and do annual cycles and so forth. Is that useful?
It's incredibly useful and exciting, the work that is coming out of the BGC Argo, the optical data. I'm very excited about Andrea's work and other people on primary production and export production, but I've seen a lot of very cool work try to understand the sinking flux out of those Argo. And I am shocked to hear that there is unclear what the future will be, because that's the type of data that maybe with the biases that it might have is still global and can constrain the model. So.
And maybe a follow-up on that. We talk as physical oceanographers and a little bit of BGC about going with oxygen on pretty much every Argo float, but FLBBs, I'm also wondering, is that this community interested, is that useful data to the same extent? They're not that expensive, unlike nitrate.
That's
fluorescence and backscatter.
I was just going to add some other groups, largely in Europe and now in the US as well, are turning on the biooptical sensors during the Purkey phase, which is also pretty useful because then you get fluxes at 1,000 meters, or you get particle composition at 1,000 meters, and I think people are starting to use it. Exciting. One comment, somebody earlier said something about the float cycling on 1 day. I just want to make the point that even though if maybe it was you, Colleen, if the floats cycle on 10 days and miss all of the particulate fluxes, any sort of biological signal is still captured by the chemistry. So I think that one of the huge values is that you have, information about particles at the exact same time and place as the chemistry itself. And I think those two things paired are actually really powerful. Yeah.
Awesome. What's up, Xinfeng? Yeah.
Oh, I want to ask you a question. Now over the past few years, there are a lot of ocean synthesis products come out, is combining ocean models and observation, like at least for the physical part, I know some product like Echo product, right? So it appears like if we add on some other measurement from the biogeochemical treaters measurement, etc., going to add on more information to those products to improve both the physics and also maybe helpful for the understanding the biogeochemical processes. I don't know whether there are plans to do that within the community.
I can speak a little bit. Maybe Tim might know more, but I know, BSOC is doing this and making GOSSI the global estimate, I think, if that's what it's called. And then, there's Echo Darwin. I guess what I don't know a lot about is exactly how they do the adjustments and if that's really informing any improvements to physics at all, or if it's just okay, that's so instead of like just fudging it over, you know what I mean, to better map it. So yeah, I think that sounds like it's in progress.
Awesome. All right, we are now at 12:03. So next up, so first up, everyone, thank our panelists. Amazing talks today. Second up, Sarah Purkey gets the award for Mom of the Day. I saw you parenting while paneling, crushing it. All right, so next up we have lunch from noon to 1. My guess is it's the same spot we ate breakfast. Then we have a poster session. Can anyone give us details on the poster session? Alyssa? Classrooms. Then after that, stay in the classrooms because we have the breakouts. If you don't know your breakout, it's in the Google Drive. If you don't know how to get to the Google Drive, find me with my iPad and I will tell you what room you're in. All right, so we will see you guys at 1 for the poster session, and then at 2, you'll be in your breakouts, and that'll be an hour and a half. All right, happy lunch. All right, everyone. Thank you all for, I know it was really invigorating breakout sessions. I am so excited about our plenary speaker, Dr. Lisa Levin from Scripps Institute of Oceanography. She was the co-founder of DOCI, which is the Deep Ocean Stewardship Initiative. And DOCI has done leaps and bounds to figure out how science can be integrated into policy and how to get scientists able to have their work tied into policy. Lisa is also one of the co-founders of DEUCE, the Deep Ocean Observing Strategy, as well as many, many, many other accolades. She's a wonderful advocate for our ECRs, wonderful advocate for science and policy, sitting at many COP meeting and UN meetings. And so without further ado, Lisa, please take it away. And also, where did you get this image? Because it is lovely.
Which image?
Your cover story, but the sperm whale eating the giant squid.
Oh, okay. Let me share my video. My slides. That is from a DEUCE policy brief, from a DOCI policy brief on connectivity.
I love it.
I'd be happy to provide that. And it's copyrighted by A. Balbar, and I'm not sure who that is, but that's the artist, I think. Okay, so let me just ask, can you see my slides? I'm not hearing anything. Somebody say yes, because I can't see anybody.
Sorry, I had to run back up to the mic. Yes, we can see them.
Okay, great. Great. So I was told I could talk about anything I wanted, really. And I'm a benthic ecologist. We haven't really heard much about the seafloor in the discussions yet. So you're going to hear about what I'll say is something completely different, really the benthic perspective on the big themes of this workshop. And so here's the topics I hope to cover if I have enough time. I want to talk about how biodiversity underpins the carbon cycle. I want to talk about the seafloor as a carbon recipient and all the different forms of benthopelagic coupling that occur between the seafloor and the overlying water. I want to talk about the critical role of continental margins and how deoxygenation and climate change may affect that role. And then I'll talk a little bit about human disruption of the seafloor and how that might affect the carbon cycle. And then if there's time, I'll talk a little bit about governance and jurisdiction challenges at the seafloor and the sediment water interface and how they're under different governance regimes. Okay, so I'm going to start with the biological pump. And we've heard a lot about this in the presentations today, and I think everybody has a pretty good understanding of what that is. But we haven't really heard about the role of the bottom and bottom ecosystems in this. We know that hydrothermal vents, which are scattered along mid-ocean ridges and back arc basins, are actually fertilizing the ocean by releasing iron. And another example of how another ecosystem that could be important in adding nutrients are methane seeps. There's some papers showing bubbles moving from the seafloor to the surface actually bring nutrients with them in the Gulf of Mexico and enhance primary productivity. And then I think maybe tomorrow there's more talk about turbulence, but it's really important to realize that the seafloor is not flat. There are tens of thousands of seamounts and thousands of canyons and probably thousands of biogenic reefs, coral reefs, for example, of cold water coral, all of which affect flow over the bottom, create different forms of mixing and turbulence that probably are important in the processes of interest in this workshop. And I thought, since we have been talking about fish and the role of fish, I'd let everybody take a quick look at what fish look like in action. This is at 400 meters. So for me as a biologist, that's the deep sea. And these are off Costa Rica. These are cutlass fish. And, we've talked about the role of fish in moving carbon down and producing fecal pellets, but also there's a lot of biomass and they hold carbon. So I'll come back to that. In fact, I'll talk about it in this next slide. Beyond the small particles, we have a lot of roles of animals in moving carbon to the seafloor, from the surface to the seafloor in a lot of different ways. We have trophic cascades and food webs that basically migrate down into deep water. We have biomixing by organisms. In other words, their movements mix water. We have bony fish producing carbonate. Actually, they poop out carbonate that sinks into the deep sea and sequesters carbon. We have what's called the whale pump, whales migrating up and down. And when they move to the surface and defecate, their feces are full of nutrients and stimulate phytoplankton growth. But we also have whales sinking into the deep ocean, listed here as deadfall carbon, and whales bring huge amounts of carbon to the seafloor. We have the diurnal vertical migrations we were hearing about earlier today in the twilight zone. And we have also massive migrations across ocean basins, from feeding grounds to breeding grounds that move carbon around horizontally. Whoops. Let's see if I can get out of this loop here. So let me go back to this diagram. If you look at this diagram, it's got a lot going on, but it's got a deep ocean floor that is flat and brown and featureless. And that's how most people think about the deep ocean and the seafloor, but it's far from reality. The deep ocean is not one flat homogeneous ecosystem. It is actually full of a host of different ecosystems, each with their own biodiversity. And that biodiversity has its own carbon, what I call carbon services. They play a role in the carbon cycle. So we have large areas along margins that are oxygen minimum zones. I mentioned tens of thousands of underwater volcanoes or seamounts. We have vast abyssal plains and many canyons and vents and seeps and biogenic reefs, and then, of course, the deep pelagic. So we've talked a lot about the role of pelagic organisms in transporting carbon vertically, but a lot of these systems sequester very high amounts of carbon in canyons, in oxygen minimum zones. The corals sequester carbon as inorganic carbonate and rubble. We have vast areas of abyssal plains where carbon is sequestered. We have carbon sequestered both in invertebrate and fish biomass. And we have methane filtered out of the bottom and sequestered in as carbonate rock by anaerobic oxidizing anaerobic methane oxidizing microbes. And I mentioned iron fertilization by hydrothermal vents. So these are just some of the carbon services provided by the seafloor. And I want to mention, for many of you may have heard of the Decade for Ocean Science. It held a meeting last week in Barcelona, and there was very good representation of the deep ocean there. There's quite a few deep ocean programs, and I've just shown they issued a statement at the very end where they list 20 or so priorities for research for the coming decade, or now it's just the coming 6 years because it ends in 2031. But I wanted to highlight that, that's my phone. I wanted to highlight that a better understanding of deep ocean ecosystems, including their vulnerability to climate change and newer emerging economic activities, came out as the third listed of those many, many priorities. So there is a focus on the deep ocean. I would like to talk a little bit about benthopelagic coupling. This takes many forms. I'm sure you've all heard the term. It can include animal migrations. They aren't just daily, but they can be ontogenetic, meaning that different life stages of different animals can live in different parts of the water column or seafloor. And many benthic invertebrates have planktonic larvae that move up into the water or even surface waters. There can be seasonal migrations. There can be transfer and coupling through food webs, and I'll give you an example of that. Sinking particles we've talked a lot about, but sinking algae and carcasses are very important flux mechanisms that we haven't talked much about. And there can be resuspension and bottom disturbance. And I'd like to focus on continental margins because, you know, a lot of the discussion has been about the open ocean, but there are vast areas of continental margins that extend around the ocean, and they account for a really large fraction of carbon burial in the ocean, estimated approximately 40%. And continental margins are complex. They used to be drawn kind of as a straight line slope, but we know that they have a lot of geomorphic features. They're influenced by land and what comes off the land. They're influenced by what comes from the up from the crust of the earth, and they're influenced by winds and atmospheric and oceanographic influences as well. So these are really complicated sets of ecosystems. And they're not all sediments, even though people will depict them as sediment-covered slopes. There are many different types of substrates, including carbonates, which lock up a lot of carbon, and basalts and ferromanganese crusts and sedimentary rock and biotic substrates. And as I said, each of these we really don't know very much about the roles of these different substrates and their fauna in sequestering carbon. But one of the things we know is that on margins, there are low oxygen zones in many of the margins, and I've spent parts of my career studying these. We know that that oxygen is declining as a result of warming. So for this audience, I think I don't have to talk about what warming is and why it causes deoxygenation. You know, it's a combination of solubility effects and stratification and less vertical mixing. And probably most of you have seen this diagram of oxygen loss over the last 50 years in the ocean. A lot of it occurs in the East Pacific, but also the Southern Ocean and other areas. And probably many of you are familiar with the idea, really introduced, I think, well, I don't know if it first came, when it first came, maybe in Bach et al., but Strama made this idea that oxygen minimum zones are expanding. It they raised a lot of awareness about this, and it's happening in all the oceans where oxygen minimum zones occur. And I've just saw a couple of really nice papers that haven't been submitted yet from investigators in China that have really good documentation of dramatic expansion of the lower boundaries of oxygen minimum zones in the Pacific by 5 meters per year. And I want to talk about what this might mean for biology. But before I do that, I just want to say that iron fertilization can cause deoxygenation. And there are some important articles that show this has happened in the past, that it might be happening now with more aeolian dust coming into the ocean, and it might be exacerbated by carbon dioxide removal. Iron fertilization is one of the technologies proposed to draw more carbon down, and I'll come back to this, but it's not a new thing. Cullen and Boyd and Yoon et al. And others have pretty much documented that oxygen consumption at depth will be increased by iron fertilization due to increased decomposition, and this will develop regions of hypoxia or even potentially anoxia below. And there's another paper, Rohr points out that net improvement in global export of carbon is tied to a net deterioration of subsurface oxygen. So I want to explore a little bit about what this might mean for the carbon cycle and for biology. And you've already seen this figure from Danielle Bianchi's presentation earlier today. I think it's a really interesting figure. It shows the depth of vertical migration of plankton, and you can basically see that it's shallower in the places of the ocean where there are oxygen minimum zones. So the whole East Pacific region, the Northern Arabian Sea, and off West Africa. So both fish and crustaceans have their daily vertical migration depths limited by oxygen. And this, of course, affects how far down they can go, consume, excrete, and so on. Now, the sensitivity of these organisms to oxygen is really remarkable. And I don't know how many people have seen Karen Wishner's paper in Science Advances, where she looked at small scale variation in oxygen along about an 8-kilometer distance. And what she found is the distributions of animals, of copepods, euphausids, and fish in the upper 400, at around 400 meters or so, totally mirrored the oxygen concentrations. You can see this here. And so over very small spatial scales, the animals are responding to changes in oxygen level. And you can see they're pretty low levels from, like 1 to 12 micromolar. Okay, so the diurnal vertical migrators are affected. And what people sometimes forget is that along margins, they actually migrate down to the bottom. And this is what the DVM looks like when it comes down to the bottom. This is 380 meters off San Diego. And you can see really high densities of krill here. And over the period of about an hour, we saw masses of krill, and then we saw masses of light fish, and then we saw, and the other thing we saw was squid. This is a whole school of squid coming in to eat the krill. So if you think about it, this is right over the bottom. This is taken by an ROV sitting right at the bottom. And it's not surprising that it affects the fish on the bottom. And my student, Natalia Gallo, did a thesis looking at the diets of demersal fishes and across the oxygen minimum zone. And lo and behold, what she found out is that when the waters are oxygenated above about 450 meters, the fish have the fish diets consist largely of pelagic species and often vertically migrating species. And it ranges from, 30% of their diets to almost 100% of their diets. And this is the percent of pelagic feeders in trawls. So she did this many bottom trawls over the course of her PhD. But as soon as you get into low oxygen, that percent changes and the fish begin feeding on benthic organisms. So the percent of pelagic feeding drops off and stays low along the Southern California margin. She looked not only at the gut contents of fish, but the stable isotopes of the fish, and she sees the exact same pattern. And what these delta N15 values tell us is the food chains are shorter where there's more oxygen, and they're longer and less efficient where there's low oxygen. And so this means that the expansion of oxygen minimum zones is going to reduce the amount of benthopelagic coupling and the effective movement of carbon down into, at least into fish on the seafloor. We don't know whether this change is the result of the fish trying to conserve their energy and not swimming up to feed, or whether it reflects reduced migration of the DVM, diurnal vertical migrators, or it could be some combination of both. Another really important effect of low oxygen and expanding oxygen minimum zones that people might not know is that oxygen affects vision in marine organisms. Vision is very oxygen intensive, and when oxygen declines, animals need more light to see. So my former student Lily McCormick studied this in 4 species of invertebrate larvae and found and basically found that that it's very species specific, but many species have their vision impaired. And what this means is that they'll change their vertical distribution as oxygen declines. So she described what she called the critical luminoxyscape, which is combinations of light and oxygen in the environment that enable visual function. And she was able to show that the luminoxyscape limits the vertical depth of larvae. Many of these larvae of squid, crabs, and octopus migrate up and down every day, but they can only migrate down so far as oxygen declines. And one of the things that Lily was able to show is that both seasonally, during upwelling when oxygen goes down, and during La Niñas when oxygen goes down, and then over time with secular climate change, all of these things act to shoal the distributions of these benthic larvae in the water column. And, nobody's quantified the effects on carbon fluxes, but again, once the animals have to dwell in shallower waters, there will be less carbon transfer. They're more likely to get eaten as well. There are other effects of low oxygen that bring benthic organisms up into the water. And I have a couple of examples here in Santa Monica Basin, almost anoxic. The snails are parasailing and all floating around in the water, presumably trying to get access to more oxygen. Here on the Pakistan margin, the amphinomid polychaetes, the worms, actually lift off the bottom and go up into the water. And tuna crabs, many of you may be familiar with them. They migrate up and down depending on availability of oxygen as well. So oxygen can basically move that arrow. Instead of just a one-way transfer from the surface to the bottom, it can also move organisms from the bottom up. Okay, I'd like to talk quickly about the human footprint and how this could alter the carbon cycle. So in the deep sea, human activities have been intensifying, and they include everything from oil and gas extraction, increasingly offshore wind, deep sea fisheries, bioprospecting, waste disposal, and spills and leaks. And now we have new activities, proposed seabed mining and climate interventions. But I want to let me start with fishing. It's probably well known that bottom trawling digs up the bottom. It has a potential to release organic carbon from the seabed. So again, an upward flex. And there are many active aspects of bottom trawling that reduce organic carbon stores in the seabed. There's a pretty nice paper in Epstein et al. That show how complicated this is. Trawling reduces the production by flora and fauna. It releases fine flocculent material and resuspends sediments and increases mixing and oxygen exposure. But there are aspects that offset these: reduced bioturbation and respiration, off-shelf transport, and increases in primary production. It is estimated that something like 50 to 60% of trawling-induced carbon CO2 release actually makes it into the atmosphere within 7 to 9 years. And people, as a result, have proposed carbon protection zones. Right now, only 2 to 3% of the seabed's closed to trawling, but there is a ban on trawling proposed expressly for carbon conservation, conserving sequestered carbon. And that's really a new idea. Bottom trawling can cause really a lot of damage. Here's a depiction of the loss of three-dimensional structure. And people may not realize that the corals and even the sponges that are damaged by bottom trawling can be thousands of years old. So this lot, in addition to loss of carbon, there's a loss of biodiversity. Oil and gas extraction is getting deeper and deeper, and it also can damage biodiversity, in particular by oil spills. And again, loss of carbon services are associated with that. Methane seeps often occur around oil and gas deposits, and methane seeps are responsible for a lot of carbon sequestration and also fisheries production. A lot of fish hang out around them, probably due to high productivity, and so the oil and gas activities can damage them. And then seabed mining, which hasn't taken place yet, but has been proposed, also disrupts the seabed directly. It can release carbon by direct physical disturbance and destroying the animals. It also releases a lot of toxic chemicals into the water, and it involves the redeposition of a dewatering plume, which can disrupt mesopelagic organisms and all the vertical migrations that bring carbon down. It can also, with noise, light, vibration, disrupt whale migrations and other large mammal movements, again, affecting the carbon cycle, but not in any way that has been quantified. So we're at a place where climate change interacts with human disturbance. We're really still trying to understand what those interactions and synergies are. But I do want to come to one more aspect of climate change, and that is the effort to mitigate it. I have just posted 3 headlines from articles that appeared in the last week or so, last 1 or 2 weeks, that tell us how much interest there is in marine carbon dioxide removal. There are 6 or 8 different technologies proposed to do this. Artificial upwelling and iron fertilization will enhance phytoplankton production, and presumably it sinks. Ocean alkalinity and electrochemical removal will address ocean acidification and allow the ocean to take up more CO2, and then seaweed cultivation and crop and wood waste disposal proposed to sink or carbon to the deep sea floor, and then there's CO2 storage subsurface. So those are some of the proposals, and they all involve using the deep ocean. See if I can move on here. I'm stuck. As the disposal target. And so the question is, how deep does all that carbon have to go? People have been talking about disposing it below 1,000 meters. Dave Siegel has this and many other nice papers that show that depending on where you put the carbon, it can stay out of the ocean, out of the atmosphere for some 100 or 200 years. There's some relatively new papers that suggest maybe you only have to put it to 500 meters to sequester it for 100 years in some parts of the ocean. So there's a lot of interest in depositing carbon into the deep sea, and all the discussions about pathways at this workshop, I think are very, very important. Also important to realize is that because of the pathways we've been talking about, is every single one of the proposed technologies will alter the biogeochemistry of the ocean and the biology of the ocean in ways that will affect the carbon cycle. So we know, for example, artificial upwelling and ocean fertilization will produce both deoxygenation and acidification, and alter food supply to the seafloor. Injection put CO2 under the seafloor, or in some cases maybe on top. It can damage a lot of animals if it escapes. Crop waste disposal and wood waste disposal and algal sinking, culture and sinking all will smother animals on the seafloor, and potentially release greenhouse gases. So there's a lot of different types, and these are only some of the types of effects that would occur if these technologies are deployed at scale. And I think, I have to remember what I was going to say about connectivity here. I mean, oh yes. I want to highlight that the ocean is super connected, and we've been talking about vertical connections and some horizontal connections, and it's connected by migrations and all the different types of pumps that we've been talking about. But we sometimes forget that what we might do in one part of the ocean will affect other parts. And I just want to give one example. Many of you may have seen this paper by Tagliabue, in which he shows that if we fertilize the Southern Ocean, we'll get increased productivity and increased carbon export, but that will rob nutrients from the tropics and the northern parts of the ocean. And as a result, many countries will have experience lower primary productivity and lower animal biomass, and probably less fisheries potential. And so all the countries you see, all the EEZ, exclusive economic zones you see in red here, and orange, are really losers under the iron fertilization scheme. And so this is an important thing to realize, that we can't work in one place and without affecting the other. Okay, time-wise, can I have a couple more minutes to talk about governance?
Yeah, we started a little bit late, so a couple more minutes good with everyone.
Okay. Okay, I really want to close with the idea that the governance of all these processes is not straightforward. It becomes important, both for scientific research and but for marine carbon dioxide removal and all the different types of activities I talked about. Many of you may know the law of the sea tells us we have exclusive economic zones and extended continental shelves that belong to countries. Those are the blue and red areas. And then we have international waters in tan, beyond national jurisdiction. And the tan areas have the seabed, the seafloor, governed separately by the International Seabed Authority, and the water, the fish in the water, governed by the FAO and regional fisheries management organizations. And then we kind of have a gap. And that attempt to fill that gap is there by a new treaty that was just signed last year, the Biodiversity Beyond National Jurisdiction Agreement, which is what it's called. But I want to show you this map of the UN agencies that govern the international ocean, because it shows you how siloed and sectored it is. Biodiversity is governed by the Convention on Biological Diversity, and then when it comes into force, the BBNJ agreement, but fisheries is handled separately by the FAO, and mining by the ISA, and pollution by the London Convention, and climate by the UNFCCC, and science by the IOC, and other whale conservation and endangered species by other entities. And so they're all managed separately. The water and the seafloor are managed separately. And so we are at a place where we have to find a way to harmonize that, because this workshop is showing us that everything is all connected, and you can't just manage the seafloor without the water, and vice versa. Okay, so these are my take-home messages. Really, the seafloor is not one system. It's very heterogeneous, and I think we do need to better understand the role of that heterogeneity in the carbon cycle. I care a lot about oxygen. I've spent a lot of my career studying it, and I think it does matter a lot. It affects many processes of concern here. The question has been raised as to whether oxygen should join the other 9 planetary boundaries. Right now, it is not. Don't have time to go into planetary boundaries. But we do know human activities are disrupting the deep sea with effects on the carbon cycle, mostly not quantified. And we have many other looming activities that could even be more disruptive. And then finally, international governance, I think, needs to better harmonize regulation of the seafloor and the water column. Again, because I've said, because they're all highly connected. So I'll stop there, see if I can get out of my slides and stop sharing. How do I stop sharing? There we go.
Wow, Lisa, that was awesome. I think it was a really great capstone to our first day of brainstorming all the different processes and how everything links together. So thank you so much. I don't know if you picked up the vigorous applause from the room over the microphones, but it was there.
I didn't hear anything.
So thank you so much. That was fantastic. We don't do questions after the plenary, right? No. Nope. Wow. So let's give another round of applause, super loud, so that Lisa can all hear us on the mic.
Thank you. I'm having trouble getting this thing to go away from my screen.
All right. Well, thank you, Lisa, for joining us virtually. Thank you so much to all the other participants that slogged through virtually. Your day today has come to a conclusion. For those of you in European time zones or who just want to get up super early, there will be a virtual breakout tomorrow morning at 6:30 a.m. For those of you who don't feel like doing that, log in at 8:15 a.m. So folks online, you can log off before you hear that everyone else here is going out to have a reception with some beers. Folks here, please join us 4 to 6 p.m. for a networking event. And then if I don't say a good night to you, I will see you tomorrow morning at 7 a.m. for another lovely breakfast. We'll be doing some more talks, some more breakouts, and some more brainstorming. So thanks, guys, for a great day.